you know, industrial type customers.
Yeah.
All right, this is great. Save it for the workshop. No, I do think we're live on YouTube now, so
it's still configuring it.
it's configuring. But anyway, just a heads up for everyone. This is being recorded now, so continue, you know, making jokes and whatever. But
we weren't making jokes. We were talking about vacuum. See, we get no respect. That's the other thing. Vacuum's good for all kinds of jokes. It's like, you know.
Hey, Avik, how's it going?
Hello. Thank you for inviting me to this.
Enjoyed your talk.
Oh, thank you. Yeah, you know, I'm ashamed to admit that I watched all the talks this morning because you know, I left it to the last minute like I do with everything.
The coolest part was the toppling of the dustbin in the end.
Yeah. So
much fun.
Yeah, that was actually a long time ago, and obviously it wasn't a very sophisticated algorithm or anything, but yeah, it was just kind of goes to show that legs give you the ability to do that kind of stuff.
Give us, you know, another year or two, and we'll be able to do that with a great deal more difficulty than you did.
Okay, all right.
Okay, who knows what we're supposed to be doing now?
Oh, we're just waiting because everyone shows up late for these things. So we're streaming this live so that this waiting period is saved for posterity. Avik, are you in Pittsburgh right now, or where are you?
I'm in Watertown. Yeah, you know, Sarah and the cats are back here for the moment. So there's a crying cat in the background, of course. But yeah, I guess we're here because my lab is open now with 25% occupancy. So
I am in the queue. I'm waiting on CMU Central to give me the thumbs up. But I'm close on my lab.
Okay.
Yeah, we got the restart thing, what, a week ago? So
yeah.
People coming in ones and twos.
I don't think we've ever done it twos.
No?
No, it's always just been one person.
Just one. I think we got maybe picked early because I misunderstood the original instructions from CMU and sent in my application, which requires a lot of work long before they actually needed it. And so I think they took pity. Ignorance pays off once again. I see Sammy. I just see his name. There he is.
Yeah, I'm already listening since 2 minutes. Great to see you.
Good to see you. It's too bad we're not really together.
Hello to everybody. Hi.
Sammy, we're just kind of waiting, I think. People show up late, Aaron says.
Yeah. Sure, I'm good in waiting in Zoom meetings.
Have you heard any good jokes lately?
I'm a very bad storyteller, so, and even worse in telling jokes, I guess. You have some?
Let me think. Just lately, I've been remembering all the jokes that people used to tell a very long time ago that one would not dare repeat now. Not that they're so awful, they're just you know, running against the grain, so to speak. It's got to be one good one. If I think of it, I'll let you know.
Great.
Okay, I think we should aim to start at 10:05. So in a minute. That should give everyone time to join.
Ankit, I wanted to ask about the platform for the Q&A session because I'd never seen it before, and
Yeah.
I wonder why you chose to go to another platform.
It allows a lot easier interaction, and I think Aaron tried this out in dynamic walking and it worked really well.
Yeah,
So
it's the only thing I found that lets you sort of walk around and then not hear everyone else in the room. With Zoom, there's breakout rooms, but you can't choose which room to go in, which is very frustrating. So with spatial chat, you can kind of move your dot around and then, oh, there's a bunch of people over there talking, so let me move my dot over and chat with them.
I think it might be really helpful in some of my classes where we have, sort of like open house presentations.
Yeah.
We tried it last semester on Zoom and it was really difficult.
Yeah, it worked really well. We'll see how it goes today. I've heard a rumor that they're going to start charging. It was kind of, I think it was like two guys in a basement, and all of a sudden everyone in the world needs different streaming options and virtual options. So they're like, oh wait, this is actually, we could make money on this. So we'll see. I think they're using it also in RSS for, what do they call them? Meetups.
The social groups, yeah.
They're the social rooms. They're using spatial chat and then also Gather Town, which is sort of similar. You still have a little person that you can move around.
So the funny part about Gather Town is if you get stuck in a doorway, then you can't pass through because it's per pixel occupancy.
Yeah, you can actually like block off sections.
That's not up to fire code.
It's really not.
Virtual fire code, that's a great idea.
It's virus code.
All right, I think we should get started.
That sounds great.
Let's do it. Aaron, do you want to go first?
Well, get your stuff together. Great. So welcome, everyone. I'm glad to see 40-something people here. With these virtual events, you never know if anyone's actually going to show up, or it's just going to be Ankit, Matt, and I just talking like we do every week at this time. So great to see everyone. Ankit's going to start the workshop by sort of giving a quick sort of background and trying to get some of the terminology and some of the context for the discussions. And especially because we don't get the benefit of having live talks, we were asked to sort of keep the live portion of this workshop to just a couple hours for sort of time zone reasons. So Ankit will give some overview, as well as sort of some background of where we're coming from, what we've been thinking about, and some of the work we've been doing that led us to say, hey, why don't we get a bunch of people together and see what else people think about these topics. Ankit, did I stall long enough? Are you ready?
Yes, I'm ready.
Oh, great. Perfect.
Okay.
I guess I should say Ankit is a PhD student at CMU, and he did most of the work for this workshop and any of the research that he presents in there. And then I'm Aaron Johnson. I'm an assistant professor in mechanical engineering, and we also have Matt Mason, who's a professor in Robotics Institute.
All right. So welcome everyone to the RSS virtual workshop on reacting to contact. I hope everyone's keeping safe and healthy during these trying times. Today at this workshop, we plan to discuss how we can make robots have transparent interactions with the world through some mechanical and software intelligence in both actuation and sensing. Before we begin, let's talk about at a high level what we mean by transparency. Transparency, as seen as in teleoperation literature, is how well the operator feels the environment through a transmission. The operator may often be a robot itself. Essentially, what this means is transparency is the efficient transfer of force and motion between the robot and the task. Let's look at an example of robotic manipulators to better understand this. This is an ABB IRB 120 industrial robot, which we have in our lab. Let me try and backdrive this. Now you can see that the robot is exceptionally stiff, even if I'm applying a lot of force on it. It is hard to move. And the deflection you see in the robot right now is basically the structural bending. This is because the robot has high reflected inertia and low bandwidth. Reflected inertia scales with gear ratio squared, and this robot is a really high gear ratio. Now let's call this configuration opaque, because you cannot transfer forces from the joints to the task and vice versa very efficiently. On the other hand, consider the direct drive arm that was developed by Takeo Kanade and Harry Asada in the 80s. In this case, there is no gearing, and the gear ratio squared term is not a problem anymore. Neither is the friction from the gearbox or the efficiency involved in the gearbox. The low reflected inertia and therefore high bandwidth make it easy to backdrive. Here's a video of that. Let's call this robot transparent. Now that we know what the overview of transparency is, let's figure out how we can add transparency in the system. The differences in the two systems we talked about earlier come down to how the actuators are configured. Let's look at a simple model of a General Electric actuator. You have the motor, and JM refers to the motor inertia. This motor is connected to a simple gearbox with inertia JG, gear ratio N, and so on. And then you have a series spring defined by K, which is connected to the load. If you were to plot the common configurations of this actuator on a stiffness versus gear ratio axis, we get something like this. The gear motor plus series elastic actuation on the bottom right pairs a high gear ratio with a soft spring, a relatively soft spring. The gear motor plus strain gauge configuration pairs a high gear ratio with a stiff spring, which mostly lies inside the strain gauge.
Hey,
And
Ankit,
yeah.
my screen is still showing that system diagram. I'm not seeing, so is that just me?
Did I fix it?
Ah, I see it now, thank you.
I'm sorry, I'm running on a small lag. Okay, yeah, so we spoke about the gear motor plus SEA, we spoke about the strain gauge plus gear motor, and now we're looking at the direct drive transmission, which has a stiff structure and a unit gear ratio. The SEA mostly is only transparent in one direction. It's really good at mitigating impacts from the environment, but not applying any forces on the environment because of the low bandwidth that comes from the spring. The strain gauge is transparent to low bandwidth forces, but not very good at mitigating impacts at all. And the direct drive or quasi-direct drive, if you get closer to direct drive, is most transparent out of these three. So one question is, why don't we use direct drive everywhere? And the answer to that is sort of, it has unfavorable scaling issues when you scale it up. Now, one of the popular ways to add transparency into the system, at least one way transparency into the system, is through compliance. And that could be passive or active. Here's an example of passive compliance that is very prevalent in most deployed robots, where to absorb impacts, you put a passive spring in series. You could also have active compliance, where you're looking at a strain gauge or a force sensor at the end effector, and you're using that to close the loop on force. You could also do this at the joint level with whole arm compliance. Here are some other examples of compliance in gripper design. And this is a combination of whole arm compliance, passive body compliance, and so on. So it's almost everything. Recently, we've seen a lot of examples of direct drive being used in medium-sized robots. And here are a few examples. The Genesis Live Drive and the Minitar are direct drive systems, which are the top two examples. And the MIT Mini Cheetah and the QDD arm from Berkeley is a quasi-direct drive system. In addition to these other examples, we've contributed to this space as well. Over the last few years, Aaron, Matt, and I have been thinking about the benefits of transparent transmission in end effectors. To that effect, we've designed a 4 degree of freedom direct drive hand, and we're trying to get this hand to do interesting dynamic and contact-rich behaviors. One of the cool things that you can do with this system is react to contact without any pre-planning. In this video, we trigger the grasp and decelerate the arm as soon as contact is detected by the fingers. You can see that this happens quite quickly. One of the other things we've been exploring is contact sensing by using velocity computed from the encoders and the system's differential kinematics. This is a very straightforward method, and here is an example of it being implemented on the mini-DAR. This is work along with Sean Wang from Aaron's lab. Now, teleoperation, haptics, PHRI, locomotion, manipulation have countless examples where robots react to expected or unexpected contacts. Ideas of transparent contact interaction cross over fields, and this workshop is an attempt to enable some crosstalk and some collaboration. To that end, we have a distinguished list of research from these areas, and we have asked their PIs to compile a list of their thoughts, ideas, and work into video talks that are available over the workshop webpage and the RSS feed group system. We have 7 contributed abstracts accompanied by 4-minute video spotlights that are also available there. I urge you all to take some time out of your day and watch these excellent talks. Over the next 3.5 hours, we will get into discussions with the invited speakers as per this schedule. Audience participation is essential, and I hope you will all be virtually raising your hands and asking lots of questions. During the discussions, please keep your microphones muted to avoid disturbances. We will call upon you to unmute your microphone once you have raised your hand. If you're not familiar with Zoom, the raise hand feature is in the participants tab. Matt, Aaron, and I will try to do our best to move the conversation along if it gets stuck.
Anka, can I just add, as a sort of Zoom culture thing, I think it's great, especially in the discussion sections, the more people that have their videos on, the more this feels like we're actually talking to each other instead of talking into a black box. So, it's up to you what you feel comfortable with, but I encourage people to keep their videos on. But your microphone off so that we don't get, sound feedback.
The contributed speaker question answers will happen in the spatial chat room where you and the speaker will all be dots, and you should be able to hear other people close to you. You can also move around your respective dots to move around the room. The speaker will be standing in the circle provided next to their poster. So you can see a picture of that on the screen. It just makes it easier to identify who the speaker is. At this point, I think we should start moving towards the first session, which is transparency in teleoperation, haptics, and PHRI. We have 2 speakers here. The first one I would like to introduce is Naomi Fitter from Oregon State University. Naomi is an assistant professor at Oregon State University working on social contact between human and robots. Here's a cool video from her talk where she is trying to do a high five with a robot. She has some interesting views, and you should go definitely look at the talk. And we have Sami Haladin from TU Munich, who's working on PHRI, collision detection, and force sensing for lightweight industrial robots. With this, I think we should take a minute's break to set up, and we look forward to having a productive discussion with all of you. I'm going to ask Aaron and Matt if I missed something and let them add on to that.
And the only thing I'd say is we've sort of nominally picked out speakers, and if we were in person, these would be the people in the chairs at the front of the room. But we're all in Zoom, so I would say if anyone has something they want to say or wants to field a question or direct a question at someone that's not one of those two, feel free to call on anyone in the room. But we'll sort of have the sort of featured panelists that we've assigned to each group.
Okay, you said you're setting up. It takes a minute.
Yeah, okay, you can spotlight people, but you can only spotlight one person at a time. So we'll have to sort of move that around for people. Ankit, you're muted, so.
Yeah, I was trying to figure out how to spotlight 2 people, but I don't think that's possible.
Yeah, you have to pick one.
Okay. All right. So I think the first. Should we just start?
Yeah, let's
Okay,
get into it. So to the audience, we have a pile of questions. We can just keep pestering the panelists, but it's much better if you in the audience, especially if you've had a chance to look at their talks or have follow-up questions to things we say, please raise your hand and we will go with your questions before our questions whenever possible. But Ankit, maybe take the honor of the first question here.
Okay. Okay, I think this covers the first panel well. So let me start with this one. The question I came up with was that there are 2 ways in which robots can be interacting with the human. One, when the human is in series with the system. For example, an industrial robot is making unintended contact with a person. Or when a robot is in parallel with the human, where you're trying to basically work with an exoskeleton. What happens? What are the differences between these 2 cases, and what are the requirements for transparency in these cases? Would be an interesting thing to discuss.
Can you repeat 2 cases again?
So one is where let's say you're in a robot work cell, and there is a robot arm that's making contact with you. In that case,
Okay.
the human is basically in a serial chain with the robot.
Okay.
In that case, you're basically making some unintended contact. But the other case is where the human is wearing an exoskeleton and your mechanism is in parallel with the human. And now the unintended contact is basically the human moving.
Well, I can start. I mean, I always think the impedance, we always talking about is impedance, and then the quintessential component is actually just inertia. We talked about joint stiffness for many years. It actually doesn't matter when you collide. When it actually matters, it's always high speed collision. Our human bodies are pretty soft. As long as we have a slow speed contact, it doesn't really matter. And then when it comes to high speed contact, it's all about inertia. And so it's all about the low inertia situation where, you know, in both cases, the low inertia will less impede the exoskeleton case and then have a lower impact and collaborative situation. Yeah, always the challenge there is like you have to sacrifice the payload and then you have to deal with the stability when the bandwidth is high. You have to always have to prepare for fast loop, and then it's mostly fast loop. I mean, there's no other good way to guarantee stability and some sort of like a control loop other than just like really fast electric system and then minimum delay everywhere.
I guess I see some similarities and some differences between those 2 cases. One thing I'm interested in understanding better and seeing the robotics community dig into more is how to orient human beings to both of those situations better. So in the industrial case, as we're introducing more co-robots without cages in human environments, sort of more intimate and vulnerable, how do we help people understand what the system's capabilities are and orient them to working with those systems? Perhaps also adding sort of expressive modalities to help the robot communicate, touch being one of them, but perhaps sound and light communication as well. In the more rehab sense, something I think is really interesting and we should dig into as well is sort of how to keep the person aware and thinking as they use the system. A kind of fun classic example of people not being engaged and invested enough is like folks falling asleep while using the Locomat system, which at this point is kind of a vintage result, but how do we keep people engaged even if there's an exoskeleton moving their legs and helping them physically move along?
I think Hannah also had something to say.
Yeah, I think the thing that comes to mind for me when I imagine a person and then sort of there's the world and then the person and then the robot versus the person and the robot operating on the world in parallel is that you could imagine the person and the robot as a spring, a physical spring. And in one case, you've got them in series, and in one case, you've got them in parallel. So depending on the relative stiffnesses of the two systems, it's going to operate as a different overall system, whether they're operating in series versus in parallel.
Can I mention something? I think there's a question about SHOs. Actually, I forgot to mention about series elastic. I think it'll be actually interesting which way is better. Like if you design low inertia system with a zero compliance, or with some compliance in both cases, with the reasonably well-tuned stiffness so that you don't lose too much bandwidth, but that in a way that contact inertia is actually not apparent because series elastic. This is always a discussion, especially when I have a meeting with the ETH, like microhudders. In this case, still, I think it's debatable, not sure which way is better in human context, because humans actually, the collision is slightly different, but when human is manipulating robot or the exoskeleton case, at least our human input is actually not that high bandwidth. When if anybody play with the series elastic force control, human input actually cannot be like at most like a 10 hertz, and then that's not too difficult to achieve with the series elastic with the compliance force sensing. So in that case, you don't feel the inertia. High-speed contact might be slightly different story, but so those two cases, maybe series elastic actually is better, but I don't know if you guys have any opinion.
So if I'm also trying to complement in a way what has been said, and I just read the question as well. So I was actually thinking that one of the questions that I thought was coming up when I also heard Anke talking about the concept of transparency. I like the idea of the robot being also the operator if it comes to manipulation, to interaction with the world, which I think was an interesting thought, which kind of connects also to the sensing problem in a way. So, I mean, there has been lots of things said about actuation and kind of transparency in the classical way of teleop, where we try to feel a remote environment as with identity metrics in a way, right? So trying to get away with zero dynamics in between. But I also think the idea of, and this is a discriminate or kind of, what's the difference between a collaborative system or a robot that is interacting or manipulating and a wearable exoskeleton is also the numbers of contacts, right? So it might be very important in an exoskeleton, maybe not yet, but I think in the foreseeable future to have really the full contact state. I mean, you are probably connected at many various points with the human. And there is the necessity to, or presumably a necessity to monitor all these contacts very accurately, which is very different in manipulators or in autonomous systems, which typically interact with, I mean, typically two contacts, right? One is at the end effector doing something, and the other one is having the collision that, or an unforeseeable contact that you want to avoid. And also in quadrupeds or any locomotion, there is primary and disturbance tasks in a way. But I think in wearable technology, this would be maybe even more complex because you have a much more complex contact state that kind of needs to take into consideration the dynamical interaction between the human and the system that is being carried. And I also like the idea kind of discriminating between, so this monitoring question in a robot where we typically assume that we are able to monitor the interaction forces, but everybody who has done it knows how complex it is to really get all the dynamics of the sensor out, to get all the real contact forces and not the one that is with all the sensing dynamics and the kind of things we actually don't want to see. And I think the concept of transparency applies there very nicely because typically it's not a algebraic relation, but it's a dynamic relation, especially if you involve observation theory and all these compensation schemes. And typically this actually gets a channel between the contact and the estimation of the contact, which could be kind of seen as a dynamic relation that needs to be made transparent. I actually like this idea, just to support the statement. And this is, I guess, a very general thing. And to answer also the question that was in the chat, or at least try to give my opinion on that. In a way, yes, of course, it's always a question. It's not an absolute statement in a way, right? So the question was whether SEA joint compliance is able to improve safety because it's already decoupling motor and link side. Obviously, this is a relative question, meaning what's the contact side? How stiff, how dynamic, what kind of inertia is on the contact side? So it's the relation between stiffnesses or reflected in impedances that you see at the contact that determines truly whether this statement is absolutely correct in a way, or whether it's only holding for a certain range of environments, obviously. But in a way, yeah, and this one of the findings on a practical level was that it's not only for SEA where we design compliances to be a sensing system as well via deflection, but it actually happened already for the high gearing and torque, I mean, having strain gauge-based torque sensing, we could see, and I think I had lots of interaction and discussions with Sangbei about this as well. So in a rigid contact, that the compliance from the harmonic drives or the gear train and the sensing already essentially becomes an SEA just because it's of the compliance. And Ankit was showing this in the deflection video, showing the inherent elasticity that we have in any mechanical system. So on a relative statement, yes, I would again support this statement. Yeah.
Yeah, I think the sense is the real force, and then the estimated, like the estimated force, the dynamics. That's an interesting point. I think in a lot of cases we it's always a bandwidth limited, in my opinion. Always stability associated with the bandwidth. If that dynamics is too slow, because of for some reason your sensor is slow dynamic, or the algorithm is too slow, or whatever, and then that basically causes instability if your estimation of force is in the loop, and then there's a delay between real force and that. And the same thing for SEA or choice of actuation or choice for application. When the bandwidth is set and the transparency is very dependent on the application. Let's say, as I said, like if a human is just slowly moving around, you can be almost as transparent as there's several ways to achieve like almost very good transparency. But once the robot has hit something, or when you're teleoperating a machine, and then the robot actually hits something, and then the transparency is a completely different story, because the collision dynamics is like way above a chart, like typically like 50 or sometimes 100, depending on what end effector has. So always a bandwidth is playing very important role. So it's good to keep in mind.
So I also have a question. Hannah, do you have a point?
Yeah, it was kind of a follow-on from what Sangbei was saying earlier about how the human system is actually pretty low bandwidth. And back to your initial question of the exoskeleton versus the robot arm in a workspace. I think one really big difference is the grounding of the actuators. So in the exoskeleton, you can actually ground the actuator locally on a person's body. And so the effective part of the body we care about is much smaller. Versus if you have a person standing interacting with a robot arm, the full body, the reaction forces are going all the way down to the person's feet. So I think the human system and the human bandwidth can change significantly based on how much of the system you're working with.
Yep, yeah, agree. Yeah, the challenge in exoskeleton is grounding on human is actually very compliant. I always make a joke like if you were cockroaches or lobster, whatever exoskeleton animal, exoskeleton problem is already solved a long time ago.
So about bandwidth, how much of the bandwidth problem comes from the mechanical inertia versus the electrical part? Our control loops plus the electronics and everything, right? Because I think the mechanical thing is much bigger.
Yes.
But I'm wondering if we can completely ignore the electrical part at this point.
Well, it depends. If you integrate a system in a way that like choose the right drivers, to the right algorithm, to the right electronics, electric bandwidth, which is typically like and at least like 400 hertz above. If your system is smaller, it's easily go over kilohertz. Compared to mechanical bandwidth, typically is set by the torque of the motor versus inertia you have to move around. It's like it can go down like a hertz or two in this manufacturing arm, and it can only go up to maybe 50 hertz. Well, it can go like 100 if it has a very well designed system with minimal inertia compliance. But and then once you include the spring, and then that can drop another like half or a third depending on the compliance. So typically, electric dynamics can be almost ignored, but there are some exceptions. If you, like, for example, I don't want to like pinpoint a product, but if you buy a off-the-shelf commercial motor driver, they tend to have a 2 millisecond delay, 3 millisecond delay, and then that give you pretty hard time to achieve like overall high bandwidth, the high stiffness, because it increases gain and it goes unstable, and then people don't know why it's unstable, and then later they found that, oh, there's a delay, I can't change. But yeah, so if you do everything well, electric dynamics is pretty much out of your question, because mechanical bandwidth completely dominate.
If I may also build on top of what Sangbei has said, so I agree. I mean, but this was a big statement, right? I mean, if you do everything right, which means you actually designed a great system, right? That's already quite a statement. And but yes, right?
Yeah, it's a little frustrating, because we've been, all these infrastructure is adapted, or how should I say, like developed for manufacturing application, where the force bandwidth is not the real challenge. So drivers, everything is designed to be just safe, and their typically bandwidth is not very high. But in certain cases like us, we have to really bring up the electric dynamics fast. Anyway, I don't want to cut your continue.
No, I actually was just trying to support what you said, just to put emphasis on how important that actually is. I mean, just 100% agreement there. So because I was, while you were talking, I tried to organize it a bit. Okay, well, how does this kind of dynamics come into account? In the end, everything becomes dynamics, right? And I also wrote electrical, computation, mechanical, delay, communication, and electrical. My comment, exactly why you were talking, was, well, it's super fast. If done correctly, everything is fine. That was my comment on my own sheet. So I can only agree on that. And I really think it boils down in the end. I mean, the same thing kind of applies also for computing. So I mean, if computing and communication don't serve the purpose, and I think this is what you meant by delay. And if you don't do the closed loop and round trip delays really to the minimum, then obviously you get a novel dynamics that, I mean, you can compensate for it, you can account for it, but you need to know it at least, or at least have an understanding of what this means for your system. So in the end, it's also a trade-off in a way, also on the mechanical side. We need to differentiate, I think, in terms of what is the open loop bandwidth of the system, right? That's not necessarily a stability statement. And then what kind of control can we achieve? What kind of closed loop control objective can we achieve given the system dynamics? And typically, if in all the domains that we just talked about, the more you know about your domain, the higher, with the right control approaches, the higher bandwidth you can achieve, right? Even for a rather compliant system, you can get amazing bandwidths if you do the right control. But for this, obviously, the identification is super important, because with, I mean, the last % is where you actually get the performance. The first 95% is always what, I think this is also something we talked about in Munich back then, is really kind of where we, I mean, you can do it, everybody can do it, but the last few % is where you actually buy the extra kick that gives you that closed loop behavior that you actually target for. So I think this is also important. So just to make this very clear, the open loop dynamics is kind of whatever the system is, we can do it great or less great. And then comes the question, what do I get if I close the loop? And then comes all these questions about which unmodeled dynamics, which ones can I ignore? And then if we do electrics, fine, yes, we can ignore that, and so on and so forth. So this is a very complex question, I would say, and really put emphasis on design. Right?
Yeah. The one that you just mentioned, the closed loop part, it is going back to your initial mention about the dynamics between the real force to your measured force. That's where, always, the delay associated with that, like, oh, I can improve your force sensing or in acceleration sensing, and then, well, only way you do that is bring up a delay, and then that, hurts our bandwidth. And then, so this is something I sent as a question, because I forgot to include in my talk, is how important to have the closed loop force control in dynamic, tasks associated with, like, include the contact, like a contact rich task. It's something I've been thinking a lot about, and I tend to choose always feed forward with the, like a lower inertia, and then just don't do closed loop, because closed loop is such a difficult to do in high bandwidth, basically. That's why and sometimes I explain people, oh, look at this humanoid, those are very slow and they're very careful because they have a ATI sensor in their foot. And then if you hit the ground, and then everything just go out the door. I don't know if anybody has any opinion on that closed loop versus, again, I think SEA is closed loop, but it's not force sensing, and then it's the spring sensing, which actually is, in my opinion, is better. I guess we haven't seen SEA exoskeleton yet. I think, and the what is that? Rethink robotics robots are actually compliant, but it's not necessarily very light. I'm still not really sure which is going to be better, or what is suitable for what application. I think is interesting.
Well, Sangbei, I've got.
I think Aaron and Hannah have their hands raised.
Okay.
Oh yeah, I had a question. But it's better to keep going. Sangbei, can you just clarify, because you sort of said, I think. Let me see if I can paraphrase. You said you think open loop is better than closed loop, but I think I'm simplifying too much. Can you clarify your statement there?
I guess that's the case where the like a lot of collision happen, like locomotion, and then when you throw your hand and it collides something. SEA can, I think Jonathan is going to say something soon. He was about to say, this SEA actually might be even better in certain cases. But again, like, I haven't seen anything like SEA colliding. I guess Jonathan might shed a light. So so far, I thought the no closed loop, because it always causes instability in high-speed collision. But maybe Jonathan can say something about SEA.
Well, I was going to ask the question. Like, sort of, you brought up two questions while you were talking. One, first, what's the difference between a series elastic actuator where you measure the spring deflection versus a series elastic actuator which just has compliance in the system, and then you have a load cell? Effectively, it'd be the same thing, right?
It's in practice, it's actually not. It's all about inertia again. So I included my talk in our force sensor. We actually, our force sensor basically designed in a way that's almost a zero inertial noise. Mm-hmm. If you grab any ATI sensor or any force sensor you have, if you shake it in the air, you basically get all the acceleration as a force. SEA measure deflection of spring. The spring inertia is very, very small. It depends on how you design it. If you design, attach a big piece of mass, and then it's not escape. But it's easy to design in a way that the inertia is very small. So SEA by nature, if you design well, it can negate the inertial noise, but not the force sensor. And typically, force sensor bandwidth is really, really high, like a kilohertz. You can intentionally add a filter to make the closed loop a little happier, but it's a lot easier to deal with as a spring because inertia is very low. That's, I think, the distinguishing between SEA versus force sensor feedback, direct force sensor. Yeah.
I guess it's all about sensor location, because certainly, like a lot of the series elastic actuators, if you put that up behind a whole bunch of inertia and mass of a leg or a manipulator, then the thing is oscillating on the end, and you can't
exactly.
that.
So yeah, that's exactly the point. If you are series elastic but your spring is very close to electric motor, then you still have a pretty big inertia, and then that's not really helpful when you hit the ground or when you hit the object. But if you design in a way that a big inertia is behind the spring, and then your contact inertia is going to drop, that's going to help not only contact, also measuring correct force.
Yeah, so for Atreus, it's interesting, our robot that had very, very low inertia on the end effector of the foot, when it hits the ground, it's great. That series spring is in the right spot. We have control of the big 160-pound center of mass of the body and can control forces a little bit. But then as soon as it lifts off the ground, and now you've switched models, a hybrid system, you've switched models, and now the series elastic actuators between the very small mass of the leg and the springs, it was jiggling and oscillating all the time throughout the swing phase, the flight phase, and you get all kinds of forces. So there was no way for us to use the series elastic actuator to detect when we're on the ground, because we're getting very large force measurements when it's in the air.
Yeah, I think I don't want to bring every discussion into like bandwidth problem, but if your actuator has a high bandwidth, you can actually cancel that very quickly. But that's not the typical case. Most of the case, high gear ratio, and you have a lot of friction, and
inertia in your motor.
You can cancel that. So that's what I'm saying. Like if somebody designed SEA in a way that like pretty high bandwidth, not too high gear ratio, and
well, I wonder if it's
yeah,
you were asking the difference, series elastic actuator versus transparency. Isn't the answer just yes? Yes, you should do both. And is it about control rates? Like you have a hierarchy of control rates.
Well, but if you do low gear ratio and then just feed forward force, the control loop is different. So if you don't have any compliance and you're not measuring the deflection like we do so far, and that's fundamentally different from series elastic and then closed loop. In low bandwidth, in my experience, series elastic is always better than like a low inertia case, because even though you're low inertia, you still need to deal with inertia. In slow dynamics and series elastic, inertia can be completely zero at some point, like not completely zero, like very, very low, you can't even feel it. So that's basically, where to draw a line and what tasks require how much bandwidth we need and so on. It's kind of interesting now.
Aaron, you have something?
Yeah, well, sorry. So this was very interesting discussion. One of the things that occurred to me is, I'm also in leg and locomotion with Sangbae and Jonathan, and so we're always thinking about smacking our legs against the ground as the like characteristic contact. And so I'm a big fan of plastic impact of, you go and you hit the ground and then you stop moving. I like it actually be more plastic than plastic. And so I wanted to tie it back to this is nominally, it can just be a free for all, but this is nominally the session on PHRI and teleoperation. And I was thinking about both the sort of the high-fiving example and other social touch, as well as from Sami and all of the sort of safety stuff of bumping into humans, of how different are any of these questions when it's contact with a human instead of contact with a perfectly plastic hard floor.
I think one thing we gotta be very careful is when we interact robot with our head, or especially your ball, that's very different from you interact with your finger. Your fingers are magic. Your hand is just magic. So as soon as you use your finger, the finger does a lot of magic trick, so that doesn't really count, in my opinion. But if you hit your arms, might be, it might be proper setting. You don't want to get hurt, and you have a skin, but that's not,
All right. So you're saying it's too easy to hit your hand, Naomi? Do you agree with that? If it's too easy?
Well, if you hit, no, I mean the entire palms might be different, but when you reach out and grab something, your fingertip, like if you do the fingertip, everything becomes easier. I mean, not necessarily high five. High five is actually pretty high inertia and surface here. Fingertip, if you do anything with fingertip, your finger does a lot of magic trick.
I do have a thought about sensing, although I think Hannah's had her hand up for a while.
I think she has a question for you.
Well, yeah, I've got a question for you. So why don't you take the ball and then I'll ask you a question.
Sure. I guess I'd second that there is some magic in the fingertip. Something interesting is kind of thinking about the set of mechanoreceptors that we have, particularly in our hands and fingers, but generally we can think about it as a sensing tactic for robotics as well. There are two fast adapting and two slow adapting types of mechanoreceptors in the fingertips, as some of you might know and have thought about. And an interesting problem in the past in some work in the lab where I did my PhD has been, how do we match robotic sensors to these different fast and slow adapting mechanoreceptors? So accelerometers are great, pressure sensors are great. It's helpful if we can get an idea of acceleration of contact, if we can do things like steady state force sensing. This works great too in teleoperation, actually. I've heard the word transparency ping-ponged around a lot, mostly with respect to kind of robotic hardware. But an interesting thing, if any of you are teleoperating or need some inspiration for a truly good operator console, is trying to reproduce a lot of those fast and slow adapting mechanoreceptor sensations through a piece of hardware you can wear. So something like a glove that I wrote about with Rebecca Kershid a couple years ago as a wearable leads to much better success manipulating distant objects when paired, in that case, conveniently with a Vicon system, which is certainly prohibitive in some cases, possible in others. You can manipulate things remotely with a robot with just amazing success compared to other cases I've seen. So thinking about those human mechanoreceptors generally, both with teleoperation and perhaps with cases where we have our robot making contact with all kinds of things, might be interesting. Slow adapting to mechanoreceptors are something I'd like to see better sensors for. I think there are some options, but they're a bit less accessible on the whole.
Should I chime in with my question? So Naomi, your talk, you said that optimal engineering solutions don't equal to optimal human solutions. I thought that was a really compelling idea, and it sort of gets to this idea that, when we're thinking of robots interacting with people, we want to be as safe as possible, which means trying to sort of maximize transparency. I wonder if maybe you're offering a different set of standards, like if we do as good as a person in terms of bandwidth, is that, I don't know, is that sort of what you would think of as optimal for the human?
That's an interesting question, and I think I'm just at the beginning of exploring some of these matters. But one good example is sort of in your proportional gain in your controller. I figured that in interaction with people, like having a stiffer spring per se, and sort of harder, more rigid contact with the person, more rigid following of sort of high-fiving or hand clapping trajectory might seem a little more intimidating and scary to people and be a bit less safe, although safety, defining that and understanding it is a whole nother deal. But we saw that as we made the sort of virtual springs stiffer, people actually felt it was more compelling and interesting to interact with the robot, and a lower proportional gain in this case made the robot seem sort of less pleasant, less energetic, and sort of scarier to people, perhaps because the motion was a bit less predictable. It wasn't as closely following the intended trajectory. But there are things to think about. I think we're still midway in the journey of defining safety and understanding how intended and unintended consequences of things as simple as gains in our controllers will influence how people perceive a robot in intimate, everyday human-robot interaction.
I think Avik has his hand up.
Oh yeah, I guess I actually had a question for Professor Stewart from her talk. So I found your hand very interesting, the parallel hand, and I thought that since we've been talking a lot about series elastic, and maybe a question about parallel mechanisms might be interesting. So so it wasn't quite clear to me from your picture, so I tried to draw out my question. Can you see it at all? It's very hard to see, but you can sort of see it. Yeah. So here I've drawn a 1 degree of freedom mechanism where if like M1 is the human and M2 is, the motor, then obviously they're kind of always fighting against each other. Whereas, a parallel mechanism with 2 degrees of freedom on the other side, obviously you need the motor to be kind of locked out for the human to be able to do anything. So I wonder which of these your mechanism is closer to, and what properties of the motor may be able to help or hurt in either case.
Yeah, I think I would have to think about it more before I give you an answer as to which picture. But I think to answer your question for that specific device, the motor is operating very slowly. You could almost imagine that it's sort of just changing the passive mechanism. And then the person is directly controlling the output of that mechanism. So they're operating at very different frequencies. So the motor is just, it's very slow, and then the transmission of forces from the output to the person is the fastest path of information transfer. Yeah, I hope that answers your question.
Yeah, thanks.
I think Yushi has a question in the chat. Do you want to ask him now?
Thank you. Yeah, Sami, I read a lot of your papers during the physical human-robot interaction. And I saw the one paper you have an overview about like a impact criterion to evaluate the impact result. And say for the impact at the head, I think you compared two results: the head injury criterion and the impact force. For the first one, I saw a lot of people have like confusions because the unit, since not unified, people have argument. And on the impact force, maybe they also have different advantages. I wonder if you can give some comments about this kind of criterion to evaluate the impact.
Yeah, sure. More than happy to do so. So this is a question regarding older work of mine, I guess. Glad that someone reads that stuff. Thanks for that. So it's a question that maybe I don't have a full answer for, but I think I have a couple of thoughts that I might share. So in general, what was the whole rise with this HIC criterion? So just for the ones who don't know that, it's basically a criterion coming from originally from the US military, self-testing in rocket sleds to understand the acceleration and deceleration limits of the human head, essentially, regarding brain injury. And it more and more evolved to becoming a criterion called head injury criterion, which essentially is an acceleration-based criterion that relates to some severe brain damage in acceleration and deceleration experiments, obviously becoming the standard criterion in automobile crash testing. And Osama Khatib and Antonio Bicchi introduced this into robotics, and there were some interesting things about metrics and so on and so forth. So originally, people thought that HIC would be a great indicator for understanding human injury in robotic scenarios, so collision scenarios. So this also kind of relates to the question of SEA and compliances in the joints, and why do we want measurements? Or I mean, it's very related questions. To make a long story short, in the end, we were able to show that HIC is an indicator for quite severe injury, so it's more for life-threatening aspects. And it happened to be that in typical robot speeds and inertias that we have, we typically cannot generate this amount of acceleration in the human head in collisions. Essentially deducing that, not that HIC is not a suitable criterion in general, just that in the robotic scale at which we move, the energies that we move, HIC is not the most sensitive criteria. That was the argument I made back then, and backed up by lots of experiments, also hitting my head several times, and trying to get an understanding of how this HIC actually plays out. The force, so HIC is kind of related, it became a kind of a criterion where people thought that this could be used for anything, and they correlated to any possible injury in humans, which it obviously cannot be, right? Because really related to brain damage or brain injury, and quite severe one typically. However, there were lots of correlations that HIC, which can be easily measured, can be correlated to other types of injuries. So this kind of made it the de facto standard in injury analysis in general. However, it was not that great to predict low severity injuries. And for example, fractures are very hard to predict with HIC. And what we did back then on the force level was that we used the force, which is indeed an indicator, a well understood and measured indicator of fractures in the face, so facial bones, cranial bones. So there is kind of fracture tolerances given certain, obviously, in impact inertias, so energies, but also curvatures to a certain extent. So they are somehow better suited to predict or evaluate fractures. However, this does not mean HIC is better or worse than forces or vice versa, but it means that given that you want to understand a certain type of injury, you need to carefully choose or find the right quantity that can be measured and correlated to this particular type of injury that is to be medically observed. And then you can build this relational chain. And I think this is kind of the answer I have on that level. It's not a kind of plain, simple answer, but I think it's kind of, the human body is so complex that it's not just reflected inertias and stiffnesses. I know we roboticists like to think that way. That's not even close to what's happening there, right? I mean, not even in the simplest kind of approximation. So it's more like, let's try to think from the human side. So an observation of injury that we can understand, and then relate it to measurements and mechanical inputs that seem to correlate there or deduce causality in an ideal case. And this way seem to be much more fruitful because you actually can predict what's going on. So it's like starting from the gold standard, which is the human injury. And yeah, that's kind of roughly in a nutshell, I guess. Answer the question a little bit?
Thank you very much.
Great. Maybe can I do one more comment on one of the discussions we had before, because I had some thoughts on that, if that's okay, regarding this SEA and let's say torque sensing or force torque sensing in the joints. I always thought, and it would be great to hear Sangbei's or Jonathan's ideas about that. So I was always thinking about SEA kind of having one inherent trade-off if we implement it with the spring only and the position measurement that relates spring stiffness and position measurement to force or torque, depending on whether it's translational or rotational. It's kind of that we kind of use the transmission as a sensor, and we need to tune the transmission to make it a great sensor, meaning it has to be compliant. Given that you have let's take the optimal position sensor we have, it is kind of limited by its resolution. So from the resolution, we will deduce the compliance that is needed to get the right torque measurement that has continuous or continuity and bandwidth characteristics. But at the same time, in order to get high controllability and fight gravity, obviously gravity is a stiffness by itself, we need to be at least above gravity, otherwise the robot always collapses. So, and we cannot do anything about that, right? So how do you guys think about this inherent trade-off if we make out of a transmission element a sensing element, and we basically have to choose then, so it becomes a trade-off? At least that would be my intuitive understanding of that. What do you guys think about that?
So the transmission stiffness, is that your trade-off design parameter? If this,
I mean, if you take SEA, right? So you have a position sensor, you've got a stiffness, And in order to get the right, I mean, typically you start with a specification for the force that you want to measure. So this is the bandwidth, this is the accuracy, and so on. So the stiffness is a consequence of the position sensing. Even if you have the best one, let's assume 18-bit position sensing, the stiffness is automatically chosen essentially if you do the right design approach. So there is no choice anymore, right? It's a consequence of the measurement requirements, and the measurement requirements will try to minimize stiffness because the larger the deflection, the better the sensitivity to force, right? But this reduces controllability and all the other things.
So
I think.
Well, go ahead, Sangbei.
No, go ahead.
Okay, so I'm thinking you're choosing the design criterion as the force measurement sensitivity. But there are many other things that could be used as the design criterion. And I think one important thing to remember is that it's always task dependent. So whatever you're trying to achieve, in my opinion, it's very difficult to make a general purpose actuator or general purpose system that is good for manipulating all things. So if you're, for example, trying to carry a cup of coffee in your friend's Humvee while you're off-roading, you want very, very low stiffness, and really what you want is something along the lines of like a Steadicam, right? Where the stiffness is effectively, what is it, 0. The deflection has very little influence on the force you're applying. Then your body can be bouncing around a lot, and then you're not going to change the force you apply to the coffee cup. And it's not actually, in that case that I'm describing, it's not about measuring. It's just about having low sensitivity in the dynamical system. On the other hand, if what you're trying to do is up against a rigid body, try to change the force that you're applying rapidly, you want it to be perfectly stiff. And so for those two tasks that you're trying to achieve, it's mutually exclusive. You can't design one actuator that's going to be good at both of those things. So if you pick a task you want to be good at, then you can choose some various, compliance ellipses and things like that in order to get around some sort of actuator dynamics that may be in your way.
Yeah, I think connecting what Jonathan said and what Sammy asked, I think the force resolution, if you use a compliance system, like low stiffness, you have a sensor resolution goes great. You can measure force because you have a larger, the signal to noise ratios get better and so on. But as Jonathan says, that's not very good for certain application. As Sammy mentioned, that is if arm is going to sag down too much. And another thing we don't include that much in an idealized world is the spring always have the limit. Spring cannot just infinitely deflect most of the case. This have a stroke limit, and then when the stiffness, either high stiffness or low stiffness, that's gonna be another driving factor when you design robot. Like, well, I can achieve this stiffness, but I cannot deflect more than 2 millimeter, and then after the 2 millimeter, it's no longer a compliant system. And same for low compliance. I can rotate 30 degree, but after 30 degree, it hit the limit. And if you have a payload, and then that series elastic might not be no longer CES because CA because it hit the limit. So, yeah, I think the sensor resolution is not something I usually think of, but eventually, what Jonathan says probably right is depending on the application, where accurate force measurement is important or not, or other passive dynamics is more important. Eventually, task is the driving factor.
I have a point to make. I think we're crossing over to the next session now, and Naomi also has to leave. So I would like to thank Naomi for coming to this discussion session. Thank you for all your input.
Thanks for having me.
Best of luck for your workshop.
I'm running another workshop today too, but it was nice to see everybody virtually and hear all your thoughts and discussion.
All right, yeah, I think we're gonna move to the next topic, which is managing impacts in locomotion. And I have a list of speakers here that I know I'm going to stop you guys from the previous discussion, but I think I'm just going to try and keep on time. and then we can come back to what we were talking about earlier. So give me a second.
Which I have to say, that last question from Sami to some of the locomotion people was a perfect transition. So thank you for that, from the previous panel to the next panel topic.
Okay. Yeah, so we have 3 people from the locomotion field who have joined us today. There's Avik, who's basically the CTO and co-founder at Ghost Robotics. Made the first Minitar, which we've all been excited about for a while, and is now making a bunch of other awesome Legged robots. Here's a video from his talk. And I think you've introduced the Vision 60 robot, Avik, in your talk this time, which is pretty cool. And then you also have Sangbei Kim, who's a professor at MIT, and he works on biomimetics and robotics. He worked on the MIT Mini Cheetah and the Cheetah, and he has a really cool demo in his talk where he's using this robot leg as a virtual magnet. Very cool, go check out his talk. We also have Jonathan Hurst today. Oops. Okay, I'm not going to play the video, but it's basically, he's a professor at Oregon State University, and he's working on the Atreus, and he's also at Agility Robotics, and he's been working on developing the Cassie robot there. Very cool work. Go check out his talk again, and I'm going to let you guys talk again and discuss. That was me.
Avik, I saw you had your hand up at the end of the last session. I don't know if you had a.
Yeah, I guess like you said, since the topics kind of blended together, maybe I'll just start by asking the question I had at the end of the previous session. So the first thing that I guess I wanted to observe from Dr. Haddadin's comment was that, the resolution scale trade-off, I guess that's, it's not just for SEA, even, so I guess we do current control for torque control on our motors, and Sangbei obviously does that as well. I mean, that has the same problem. So we have current sensors, and those also have that same resolution scale trade-off. And to some extent, I guess there are technologies that let you adapt the scale online. So that could be something that could be an interesting thing to consider in that aspect. But I just wanted to make sure, just wanted to say that that's not an SEA specific problem. We have that for direct force control as well. And the other thing that I actually made me want to ask the question in the first place was, Dr. Hurst's example of the coffee cup when in the Humvee. So you presented it as perhaps an example where kind of just being passive and having a low impedance might be good, but actually it seems to me that you need very high precision tracking, like the Steadicam that you mentioned, that actually has very high bandwidth tracking controllers to keep the cup upright. So it's actually maybe a very interesting task to talk about the trade-off between being loose and being stiff, I think.
Well, the Steadicam can be entirely passive, like no electricity. Just a physical spring that's a very, very, very long, soft spring that has been stretched to the point where it's applying the same force as the camera.
Yeah.
Or, as you say, you can have a direct drive motor and implement that exact behavior in software. If you have low inertia, right?
Yeah.
If you've got the right kind of bandwidth.
Yeah, but to support like answer Avik's comment and support Jonathan's idea, because the cup and that Humvee situation, any closed loop control is going to kill the bandwidth, and it's not going to work. That's why you want to have the mechanical system deal with it first, and then we'll let the control algorithm to be slow. So you have to be careful, like, always high bandwidth is not always good, because if it depends on task. Basically, that's why I said it depends on the task.
Can you define bandwidth for me?
Sorry.
Can you define bandwidth?
Patrick came the closest to actually having a definition their TRO paper. So maybe Sangvi should answer this.
Say it again, like the bandwidth. I can give you a simple example. I mean, this is happening all the time, and it's done in the haptics community, the bilateral teleoperation community in the 90s, Hannah Ford and many other people. When you want to make a contact, I think it's very similar to leg locomotion, and you want to plant a foot in the ground. I want to have a force sensor here, and then as soon as I hit the ground, I want to keep the force 10 Newton, for example. So closed loop, maybe you detect the contact and then keep tracking force of 10 Newton, and then it doesn't work if you don't do a lot of tricks, because your force bandwidth, sensor bandwidth is like kilohertz. It depends. So if you had a rower, maybe it's 50 hertz. Your actuation bandwidth typically is like less than 10, unless you're really strictly designed it. So it goes unstable all the time. So that's what I mean by you gotta be very careful choosing which part should be closed loop, which part you just let the mechanical system deal with the high dynamics. You know, like we include full dynamics and then acceleration force all the time, but it doesn't work in high velocity intact, because there's no actuation can handle that kind of speed, and then the shock wave travel at speed of sound. So, you know, even though we have a zero delay, the force will travel within a millisecond.
Well, I it's like maybe it's a slightly trick question. I mean, I think of a physical spring. It doesn't have infinite bandwidth, right? Even a physical spring, if you say I want it to be F equals KX, that's my thing I'm measuring against. And now at what frequency can it do F equals KX? Well, there's actually a roll-off, because that spring has some inertia associated with it that's going to make it not do F equals KX. But the physical spring is going to have a pretty high bandwidth compared to any sort of active system that you've got. So, and it depends entirely, again, on the task that you're trying to achieve. So that, so you described an impact, a specific test, specific test that has to do with impacts, and then whatever your system is, you know, a goal of can you achieve it or not, I guess.
Yeah, so task has some bandwidth associated with that.
Right.
and you know, if you have a closed loop or if you have a spring, and then there's a natural dynamics, which would basically limit your control bandwidth as well. So it all depends on which task. So
I've got a question for everybody then. You know, we talk about the fast adapting versus the slow adapting mechanoreceptors, which is really interesting. We talk about whether we should be doing just straight transparent transmissions and do all of your sensing, say at the electrical dynamics, which is typically very fast. You can do a very fast control loop on the current of your motors, and you know, these direct drive machines can be very, very good if you've got low inertia. And so at a small scale, like at the Minitar scale, you can get really good dynamics through your software. But as you scale up, you can't. And so the actuator dynamics get in your way. We start thinking about adding things like series elasticity and everything else. But I wonder if it all comes down to staging control rate hierarchies. You know, what's going to happen at a very fast rate and very low information, what's going to happen at a medium rate, and what's going to happen at a much longer rate. Because like with Atrius, at least my team controlling it, could never do force control on the ground with it. It was just straight up sending, position controls feed forward through the motors, and then when it impacts the ground, we've got a set of dynamics that are designed partly in hardware and partly through that feed forward position and partly through low gains. So about 50% of the leg deflection was a proportional gain in the software through all the friction and inertia of the motor, and the other 50% was through the physical springs. But we couldn't do anything like detect ground contact, for example, because I mentioned, the legs oscillating in the air. And when you hit the ground, you don't know for a long period of time. But we did, at a very slow rate, like 30 hertz, maybe 50, determine when it's on the ground or when it isn't. So there were a bunch of things with different filters at different layers. So I don't know, what are your experiences? Sangbe, you've got this really incredible sensor that you've been working on for some time on the end of the a very transparent transmission and leg. How do you use that combination of feed forward through transparent transmission and that feedback? Are they at different control rates? How do you integrate those two?
Very good question, but it's a little complex.
Yeah, there's a lot of pieces there.
So let me start with the direct drive idea. Yes, I think I mostly agree with you. Like small scale, it's easy to make it stiff, and then, but the electric motor doesn't scale very well if you go down. So I'm not really sure torque per inertia number is good in small scale, but I agree with you in the stiffness is so much easier to achieve. But the way the robot get bigger, that like the achieving the high stiffness is such a difficult thing. You probably know better than me. You know, even though you try all your best, I want to have a zero compliance. It's if you have a transmission, it's even harder. So even though you try all your best, the end effective force bandwidth is going to drop down easily 30 hertz. But that's, I think, is a fast side of the story. If you look at all kinds of robots in the world, 30, 40 is very exceptional. Most of them are like less than 3. So we've been living with it. Like our mini Cheetah is probably the best one. It's like 50 hertz force bandwidth, and then inertia is pretty low, so it can handle impact. We don't do anything in the impact except the detection. So it's binary. The force sensor we are developing, again, I'm still against closing the loop on the force magnitude. The virtual magnet demo, if anybody guessed what's going on behind, there's no magnitude force feedback going on. It's all feed forward. And then feedback is actually only location. Because if you, as soon as you start closing loop, the question you ask is going to bite your butt. You know, the staging frequencies and that's going to limit your performance. Like I want to have everything, I want to implement every pieces in my equation, and then if you throw in the robot, in order to make it stable, you're gonna stage such an unimpressive, you know, behavior. So
So your sensor is giving you a binary direction of where the force is being applied, but not a magnitude.
Oh no, this force sensor is a 5 output. It's an XYZ force of the one, you know, estimated contact point, and it also gives you the 2-axis point contact point where in the hemisphere. So we only use the normal force, even though you can measure shear force, because normal force is most you know, apparent to the thresholding. So if you have some impact force or force is above 2 Newton, for example, now I'm going to initiate the tracking algorithm, which is literally I'm going to just push in a direction where I'm in contact. So the feedback is only contact location. So if you think about, I'm pushing 10 Newton in a direction when it's in contact, it will just follow me all the time. So if your force sensor is reasonable bandwidth, our force sensor have a kilohertz bandwidth, and then our actuator has like 50 hertz bandwidth. My hand is moving probably at most 6-7 hertz. So your you know, basically in this case, task bandwidth is about 5-6 hertz. If your control, your overall dynamics is above 40 hertz, and then that's good enough. And it's still, I don't want to have a feedback because that can resonate in many different fashion. You know, the rubber, you know, bouncing can be, you know, in a ballpark. So we always do that. Make sure if you do force feedback, we're gonna make sure like that rule of thumb, like hopefully 2 order magnitude, or at least like 20 times faster, so that we can have a room to play in the gain side.
So you actually just control forces by controlling the currents in your motors, and use the toe as primarily a knowing when you're in contact and when you're not, and which direction that contact is and where it is.
Exactly. So still feed for force control, and this contact force can be used for manipulation or even locomotion. The initial motivation was a locomotion because we don't know the surface normal of the contact when you're, and then this force sensor will give you the surface normal, and then it will give you a much better cue for contact detection than our force observer. Observer is really terrible because there's a lot of shaking.
I think Hannah has a question, and then Aaron.
Yeah, I just wanted to bring up sort of, we've been referring a little bit to human cutaneous perception as a potential analog for feedback control. And I think we do have to be a little careful sort of taking inspiration from the human system, just because our cutaneous sense comes from, some evolutionary, reasons. It might be because touching our loved one made us more likely to survive, right? So it's not necessarily only going to be helpful for high impact circumstances. I would even say on a more mechanical level, a lot of our fast acting receptors are for very light touches like rubbing. So you get vibrations that are high frequency, but not necessarily high force. So fast acting doesn't necessarily mean large mass, large MA in terms of the dynamic sense. We do have heavy touch, fast acting pressure sensors, so they might play a role. But I think we just need to tread carefully.
Yeah. But we're terrible at knowing how much force we're applying with the muscle, aren't we?
Again, I think it's a resolution accuracy. I'm not really sure, but our perception, if you touch something, the force control is mostly done by muscle feedback, urgent-tendon feedback. So I often say that your skin is very sensitive in vibration, as Hannah said, and there's a stretch sensor is good and they're slow, but eventually force control is mostly proprioceptive, in my opinion. I make a joke, if you change your shoes and then tie your shoestring really hard, you have to recalibrate to run. It's not the case.
Aaron?
Yeah, so that discussion, we talked a lot about sort of force sensors. And when I was watching the talks, I think all of the locomotion people said that they didn't really use contact sensing, they didn't use tactile sensing. I'm a big fan of proprioception, that's all great. But it seems like it would be nice to just have a sensor there that tells you when you're touching the ground. And so a couple people said, oh, if you smack your sensor against the ground over and over again, it's going to break. Is it a robustness issue? Is it a sensitivity issue? Like if you had a perfect tactile sensor for your foot, for your robot foot, would you guys use it? And I'll direct that to any of the Jonathan, Songbei, or Avik.
Well, I mean, we haven't used it, but many other people use already. Like Unitree guy's been using all the time, and I guess Boston Dynamics is not really tactile sensing, but they use the force sensor to detect the ground. I will use it if you have a very robust sensor, and I agree with you. We should use the force sensor to detect the contact because observer can be terrible. I just want to add another thing about the mechanoreceptor comment from Hannah. I think the high vibration sensing, which is high frequency sensing, mostly for the rubbing and like detail, dynamics, I think is critical for like locomotion as well, like sliding, like slip detection. We just don't know how to yet. We're not bandwidth in terms of research bandwidth is not good enough. So, but I think if somebody can come with it, I think it would be great to detect sliding and detect, like if you hit like sand, for example, and then sand, you're gonna always slide on the sand, and how to characterize that with, what tactile sensor, our force sensor probably cannot do. So we need something, give us more detail of that contact dynamics. That'll be interesting, I think.
What did you say exactly, Aaron? You said if you had a perfect force or contact sensor that always worked and didn't break, and would we use it?
Yeah, I mean, you can put as many idealities in there if you want. I mean, but it sounded like a lot of the discussion in your talks, at least the way that you guys wrote off the sort of contact sensor at the foot, was a robustness issue of just if you smack it against the ground, it's going to break. Is that the only issue, or are there other issues?
No, I wouldn't even use it if I had a perfect one. I just don't think it's particularly helpful. I think what really matters is not everybody focuses on that point of contact. And this point of contact is also why a lot of the simulations don't match the robots. You know, the contact dynamics aren't right in the simulations. They're never perfect. But, you know, running through the world, it's not perfect, of course, either. And really what matters is how much is the forces that you're applying sort of on the scale of an entire stride. And so applying those forces, even if your end effector, if your foot is moving around through mud or through sand, or whether it's made contact or not, you know, you want to be able to apply the same amount of impulse on average throughout your stance phase. And I think that has a lot more to do with just, I don't know why it should matter why you're on the ground, or when is that specific point you're on the ground or not. I don't see why that should matter very much.
Yeah, I guess.
Yeah. Sorry.
Yeah, I guess my response would be, yeah, robustness certainly, you know, in our personal experience was an issue, but I agree with sort of what Jonathan said. Even if someone built a perfect one, I don't think we would want to use it for a few reasons. One is, you know, obviously, you know, it adds cost and like wiring complexity and things like that, but we'll ignore those as not being fundamental issues, let's say, even though there are definitely practical issues. And the other thing is, you know, they kind of localize the sensing quite a bit. So for instance, you know, the legs can be bumping against the wall or things like that. Obviously, that's difficult to do even with our proprioception to kind of identify where the contact is happening, but it's not impossible. Whereas it would definitely be impossible with a toe sensor to be able to detect, you know, unexpected contact with, you know, the shins of the robot or things like that. Yeah, I guess so. So and lastly, I guess, you know, animals, we were talking about kind of human sensing. I'm certainly not an expert, so I try to avoid pontificating about animals, but you know, certainly we can like walk on shoes and stilts and things like that and do just fine. So, you know, that shouldn't be any reason for us to embrace contact sensors.
Yeah,
I'll definitely use it. Yeah, sorry, I make it sure. I'll definitely use it for contact, like a simpler information, not for closed loop, if it's the robust. Go ahead, Anna.
I just wonder about what is the nature of the information. So there might be some information that is totally redundant to what we could get from the muscle or higher up in the system. There might be some information that is just really helpful to get from the contact point, kind of like Sangbe said, well, what about sand or slipping or these other situations that we just haven't dealt with yet. So, and I also feel that there are ways, you know, if you decide, well, we don't care about force, so we're not actually measuring force, we're measuring some other physical parameter altogether, we could start to think outside the box about how we measure that, maybe even remotely or really robustly. So yeah, I don't want to, you know, say that force sensing is the only thing we could do at the contact.
For sure. I mean, actually, if you're walking outside and then if you're walking in a cold river, you still can, but it gets harder when your feet get numb. So I think there's a lot of things about that, you know, sensing the grip that you have, and other things that, at least at where we are with legged locomotion, they're like the third problem away from the one we're trying to address right now. So someday, but for us, just getting the basic dynamics to work really, really well does not require the force sensitive or any sort of sensors on the foot at all. And then creating the dynamics of the system that doesn't care about the contact point very much also makes it robust to significant errors and disturbances in when or where or how that contact happens. So if you create a system that, you know, the ground is higher or lower or softer or stiffer and it doesn't matter, it also works really well in simulation, and you get a good correlation then between your simulation and your reality, because one of the major sources of noise, your whole dynamics of your system is just robust to that source of noise. So we're paying a lot of attention to what are the things we actually do care about and what are the things that we want to make the system robust to. That's actually a really tough question.
I'm going to chime in here, and I think Johannes has a question.
Hi guys, I'm Johannes Engelsberger from DLR Germany, and I have yet another question to Sangbe. Actually, I think I understand you right that you would wish for a like pretty much infinite, like lightweight robot like leg. That's right. Mm-hmm. For like perfect proprioception. However, for like swing leg control, I would be super afraid of like having no mass, because then like no matter what like PD gains or whatever you choose, you would have like infinite eigenvalues to control this thing. You see what I mean? Like if it's super lightweight, maybe even your electronics is not fast enough to get this like controlled.
Well, I doubt that that's going to happen in this world. Maybe in the other world, no matter how light it is, your mechanical bandwidth is going to be at least one order magnitude slower than electric dynamics. So,
okay.
Yeah.
Even for like super stiff.
I wish that happens actually, but no. I guess it can happen if you go down the scale.
Well, think of a hard drive.
Yeah, that's down the scale basically, small scale where the mechanical bandwidth is like getting close to electric dynamics. It's not like 20 times slower. So we need to worry about many other things. AFM is basically the extreme example, I guess.
Actually, I believe that like very much depends on the chosen stiffness. So if you want to make like a very like light finger be very stiff, I would believe that like typically like what we work with is like 1,000 hertz of control bandwidth, and then I would propose to like try to like get like stay away from like anything that's higher than like eigenvalues of like 100, like a tenth of, you see what I mean? And like depending on the stiffness you want to produce, it very much becomes a problem in this world. But maybe the stiffness values that you choose for your application are far from this like super high eigenvalues then.
Well, so you're talking about control rate, and for sure, yes. if the hardware dynamics go faster, your control rate needs to go faster. I think on a hard drive is the example I suggested. I think use a lot of analog circuitry in order to make sure that control rate is very, very high. Also at Mecha Robotics, they had very nice series elastic actuators in those joints. And they controlled they increased their switching frequency of their PWM to 100 kilohertz. Traditionally, these PWMs are like 24, so you can't hear them, but the lower the switching rate, the higher the efficiency. Well, they pushed it all the way out to 100 kilohertz PWM, so they could increase their control rate fast enough because their mechanical dynamics was getting fast. So yeah, you can run into those limits depending on the scale and size.
Which part make it that fast in the series elastic?
I don't know, actually. I was skeptical.
That's skeptical, yeah.
Well, me too. But Kevin Kemper, who was there, and making these things, and I said, well, come on, 24 kilohertz of the switching rate and a kilohertz control rate ought to be more than fast enough for your little motors there. And he's like, he showed me the difference. He's like, well, here it is, at this rate, and here it is at this rate, and you could feel a difference.
I gotta say, if there's I'm pretty sure there's other control loop is not designed properly. If the control loop is not done well, then the bandwidth of the PWM matters. Yeah,
it's an engineered system. Who knows what's optimal? I don't know.
Yeah.
Hi, this is Peter Whitney. I'm on the phone.
Hey, Peter.
Just wanted to jump in about PWM rate. I mean, that's usually associated, especially with small motors that have a very small winding inductance. You get a lot of current chop unless you have a very, very high PWM rate. So for small scale systems, especially like Maxon motors, Maxon motor drives usually come with big honking inductors inside that actually add additional inductance to prevent this current ripple. So
that must be right. Thank you.
I think and I think there's high PWM rate is also becoming more interesting. There's new, I think like gallium nitride MOSFETs that have extremely low switching losses, and so people are starting to look at high PWM rate also for efficiency.
Yep. So Mecha Robotics probably use a small Maxon motor, so that must be the reason.
I've got a question, maybe for Matt Mason. Surprised, did you think anybody was going to ask you a question today? But anybody. Has anybody really used a series elastic actuator successfully in an application? And
in commercial setting, you mean?
In a
You mean
commercial setting,
commercial. Yeah.
a useful setting, right? I've seen a lot of series elastic actuators in research, and they show performance in test scenarios and things like that. But they have so much baggage with them in terms of the oscillations and the control and the complexity and so on. Has anybody used one usefully, commercially or otherwise?
Yeah, I don't know why you're asking me that.
Look at your T-shirt right there. It's like you're working at a real company now.
Oh yeah, I forgot. I mean, I couldn't name one, but that's not saying a lot. Actually, I'm kind of, maybe I'm too simple-minded. Oh yeah, the Baxter. There's one, right? I was going to say I might be too simple-minded because I look like, you know, when I look at an ATI, I say, well, that's a spring and a. So I'm still struggling with the argument about whether it makes sense to put a series elastic actuator together with an ATI, because an ATI is a spring. It's just a very, very stiff one.
What's an ATI?
Oh, it's a force torque sensor, you know, that's made out of.
Sensor, yeah.
Right.
So I have a kind of simplistic attitude towards these things, but I think the right answer for me was I didn't know one, except, you know, the Baxter would be an example. What else?
I have a push lawnmower that has a little spring on it. And when you push it, the wheels go faster, right? So that might be a series elastic actuator, controlling the position based on the deflection of the spring.
And I think all the legged robots, we put rubber on the feet. And
yeah, but are you measuring the deflection of the rubber and closing the loop around that?
Oh, yeah. Right. You want a closed loop on the force control, as opposed to the. I mean, right, there's the sort of control question as opposed to the sort of passive dynamics question.
Right, right.
I believe there might be some manufacturing application. They add compliance at the end effector and then measure that to ensure the right force. If you want to do something fast. If you do something slow, like a welding, spot welding, they actually use a force sensor to do that. But if you want to push something, I never seen it. I'm just wondering. I'm pretty sure there's a lot of compliance to use and then set the accuracy to make sure the force. But I'm not sure they do closed loop. But they might not.
Like the remote center compliance peg and hole thing. A lot of compliance is used. Just the classical series elastic actuator as originally envisioned.
I never seen it. Yeah.
I wonder if active suspension has some elements of series elasticity and closing the loop on it.
Active suspension in
cars?
In the commercial car or the research car, like Bose?
Well, I think there's a lot of active suspension in commercial cars now.
I'm
sure
most
all the
commercial
Ferraris and all of them have that.
Most active suspension doesn't have series actuation, mostly parallel damping adjustment mostly. And series, you have to generate that force constantly. It's not realistic. That's the Bose case. That's why they never get commercialized.
Maybe take a question from Rohan. Has his hand up.
Hey, can you hear me?
Yeah.
Great. So I was just, trying to follow this whole trail of thought regarding series elastic actuators versus, ATI. And we talked about, how the resolution at which we can measure the position deflection being one metric to pick. And I sort of agree with, Matt Mason's perspective where we can just think of ATI as a super stiff spring. And basically, if you have a strain gauge, that's like a very high resolution position deflection measurement. So, you are able to get like high accurate force measurements out of the system. And I'm trying to understand if we have, such a sensor available at our disposal. And if you're working on an application where electrical dynamics are significantly faster than these mechanical dynamics, then is just going with a 6-axis force torque sensor a clear win against series elastic actuation, because you can bring all that compliance directly from the software. and all the passive dynamics arguments that you've been making that could be implemented in software, right?
Yes, if you have a sufficiently transparent actuator that has very low inertia, very low friction, all of those things, write a proportional controller for whatever stiffness you want. There's no good reason to put a physical spring on there. If you're measuring the current, that may be a really good way of measuring the torque that you're applying. Or you can put, a load sensor on there. It becomes an engineering choice at that point. Would you rather you measure the deflection of a physical spring? Well, if the only behavior you ever want is that particular compliance, then you might as well use a physical spring. There's no reason not to. If you want a lot more flexibility, then of course it should be in software. And then do you get better sensing with current control, or do you get better sensing with an ATI force torque sensor? It depends on the application. But I think here's a big question. What happens when you hit that with a hammer? If it's a industrial robot arm with an ATI force sensor on it, if you're pushing on it slowly, it's going to work great. But when you hit it with a hammer, it will just immediately break because of all the actuator dynamics, the inertia of the motor, and then so on.
I see. So it's basically a bandwidth argument at that point.
And it can also physically break the ATI sensor.
Well, sure. So if you get enough force on it, right? But if you had no inertia behind the ATI sensor and you were to hit it with a hammer and it were to instantaneously accelerate, then you wouldn't get a high enough force. So it's.
If you hammer with steel hammer, you can easily generate above 10,000 Newton. You can break the bridge, crack the bridge, or deflect the bridge. It's very easy to generate high force if you don't have any contact compliance.
I think at this time we should break and go check out the contributed posters on the spatial chat room. I think we were supposed to do that at 11:45 until 12:15, and then we have a break after that for about half an hour for lunch, and then we will meet back here at 12:45. Does that sound good to everyone?
Great.
And also, I'll keep the Zoom room open so you can continue socializing here. Ankit, in a moment, can you send the spatial chat link in the Zoom text chat so
I
that
will do
everyone
that.
has it? Everyone has it handy to go.
It's also on the website.
Yeah.
So you can go look at it there, but I will send it to everyone. Right, great.
Spatial chat.
Thanks to whoever were the official panelists. Forgotten.
Yeah, great discussion this morning. We'll have another panel at 12:45 Eastern. So that's 9:45 Pacific in Oregon, where this conference is happening, I guess.
Yeah.
And I'll see everyone over in spatial chat as well.
Spatial chat. There it is.
What is it about?
Sunbay, are you mumbling?
Yeah, I'm logging in, but not sure what I'm doing.
All right. Depending on your operating system and browser, you may have to leave Zoom so that your browser can get the microphone and camera.
Yeah, Windows.
Some people can do both at once, and then it gets kind of confusing. So anyway.
Maybe I'll close this because otherwise, whatever I'm saying on spatial chat is also going to go into the Zoom room. Is that right?
I mean, you could mute yourself. But...
Well, that would be.
Welcome back, everyone. We'll give people a few more minutes to file in. Okay, in the interest of time, maybe let's start the introductions here, and a couple of people will still file in, but I want to get to the last discussion group.
Okay, awesome. For the last discussion group, we have the topic of transparent sensing and actuation and manipulation. And you find a window there. Okay, great. Oh, okay. I forgot to mute this, but that's fine. Yeah, the first speaker we have today is Hannah Stewart. She's an assistant professor at UC Berkeley. And in her talk, she's explored multimodal contact sensing for manipulation to improve transparency. One of the coolest things I saw in the talk was the use of vacuum as a tactile sensor. And I think you should go watch the talk whenever you find time. The other person who will be in the panel today is John Whitney. He works on hydrostatic transmissions. He's an assistant professor at Northeastern University. And I think the highlight of his talk is when he tries to get his teleoperation system to use the straight edge razor on his face, which was really cool. Daring, I must say. And yeah, I think we can start now. There's also a really cool demo of transparency right here. I'm going to stop my screen share and then we can start talking. All right. Maybe wait a minute or so for everyone to show up.
I don't know. Let's go. We're supposed to sort of keep the workshop to only so much time, so we're just cutting into good talking time. Looks like we've got one hand up from Theo.
Hey, I have a question for Hannah. Basically, I was also interested in the suction gripper that she had and the use of such suction grippers for sensing in the air, not in the water. I think there was a discussion with Matt at the beginning. Maybe if you could say a few words on this, if it could be only binary signal when we are in the real space or could be more rich. Thank you.
Sure. Yeah, it's a great question. I get it almost every time. Well, we worked with underwater just because that was our application, but I think you could totally think about how it could translate into air. It is a different fluid. So water is going to be more viscous and also just denser. And so if you look at the sort of drop off or the change in flow rate as you've got like gap heights between the fingertip and the surface, suction flow will change significantly within like 1 millimeter underwater. So that means that gaps are going to be at least an order of magnitude or something. It's going to be much, much smaller if you're at the same flow rate. So you're just going to have to charge everything up. So higher max flow rate. You're going to have to play with the system if you want to use it as an analog sensor of flow. Of course, when you start pulling the flow rate up, you're going to have a system that wants to, when the gaps are very small, go into stability. So I think in general, you're going to see your systems look more binary in air. So I think the analog reading is just more suited to a more viscous fluid, but it's not impossible in air. I just haven't done it yet.
Cool, thanks.
I have a question for whoever wants to answer it, I guess. But I think this is something that that John brought up in his part of the talk. And I think he was looking at what is the right figure of metric for SEA parameter selection. But I think I want to ask a question slightly above that, which is to say, what is the right metric to say if a system is transparent or not? And I know the impact factor is a good way to do that, but are we missing something from that description, or is that complete? Is, I guess, the question.
Is Peter here? He might be a good person to take.
Yeah, I'm here. I think I shared the same question actually, and I'm not sure that I have any good solutions. I mean, the way that I think about it is, you know, if you have a series elastic system, or I mean, all systems are to some degree series elastic. You know, if we look at the endpoint impedance, you know, that impedance is going to vary as a function of frequency. And you know, when you have an impact, you know, when you touch something, and I mean, I think even just, you know, taking your finger and tapping on something is actually a pretty significant impact. You know, it's we can think about the overall mass of the system, or you could think about, well, if I have a soft spring, then I'm mostly just feeling the endpoint mass. But then to Sangbei's point in his talk, well, you've also got damping, and so damping, it doesn't increase with frequency, but it stays constant, and so it can be a very significant factor. And so, I don't know, I find myself just sort of looking at the full, you know, Z as a function of omega, and then trying to reason about, you know, what region, what bandwidth, or what region of frequencies are important in different situations, and then just sort of look at the overall impedance. And I'm not very satisfied by that approach. So I think maybe Sangbei and others have done more to think about an actual quantifiable figure of merit. But yeah, I agree. I don't think it's as simple as, you know, oh, what's the endpoint mass, or something to that effect.
In your talk, didn't you say that it was all about the mass? Am I mixing up which talk was which? Didn't you say it was just mass?
Yeah. So I mean, so for series elastic, I mean, this is a big question, and I in the previous section, you know, it was brought up like, hey, who has seen series elastic used in practice and in a way that really satisfied? I mean, so in my mind, series elastic is about one of two things. First of all, it might be about actually storing mechanical energy, and this is actually going back to how it was maybe originally envisioned, right? If you have a cyclic operation like running, and it might be more efficient to store elastic energy rather than try to recover that energy electrically, although people are doing better and better at that. So that's one class of SEA. But the second and perhaps larger class is it's merely a way to hope that you can cover up for a high actuator impedance. And so it's really all about serial chain mechanisms in which your endpoint mass is very, very significant in terms of the overall inertia of your system. And so electric motors have pretty much a hard limit on the torque density that they can deliver. And so if you want many degrees of freedom in series, you're forced to introduce a gear ratio. And so the idea of SEA is to say, well, you know, as I get more and more friction, and as my actuator impedance gets higher and higher, is there a way that I can sort of cover up for this? And so the very simplest way to do this is to say, well, if I want to do some kind of force feedback, so if I'm either measuring the force externally with a force sensor, or if I'm using the sort of quote unquote proprioceptive force from the spring compression, I need my mechanical bandwidth, and I think Sangbei has got a really good way of thinking about this. I need that mechanical bandwidth to be low enough if I'm going to be doing some kind of admittance or force feedback. That mechanical bandwidth needs to be less than the electrical or closed loop bandwidth of the system. And so that's sort of step one for SEA, is to say you're just sort of adding some physical compliance, and that buys you time. You know, that buys you a little bit of phase margin to have a chance to have the system be stable under force feedback. And then the open question is well, then should you go further, right? Well, are there cases where you'd want the system to be even more compliant than that? And to me, I don't know if there is a case for that. I think that series elastic is just primarily about trying to make the best of a bad situation, meaning, you know, high actuator impedance. And yeah, I think that it's not clear to me that it in and of itself can be, you know, offered directly desirable properties. And so to this question of it's all about math, you know, one argument about how well SEA could be, you know, sort of better than not using it would be say, well, if I have some significant compliance, then I'm decoupling my actuator mass from my endpoint mass. And you can imagine having some kind of a force feedback and state feedback. You know, the simplest way to imagine it is you're going to program the actuator mass so that it directly tries to track the endpoint mass, such that, you know, in theory, as you interact with the system, you're only ever going to feel your endpoint mass and inertia, which, you know, in theory could be made much, much smaller. But I don't know that this actually works out in practice. I think that, you know, if you actually are going to implement force feedback and you're going to try to hide a significant amount of your actuator mass, I think that, you know, in order to maintain stability in all cases, and in particular in the case of impact or coupling to a rigid environment, I think that there's not too much that you really can do in practice. I think that the cases where you look at that force feedback and you say, hey, like it's really increasing my transparency, that's only in sort of the artificial case of I'm grabbing the manipulator and I'm, you know, moving it back and forth. And so yes, when I'm, you know, when the motion of my arm, which is only, you know, maybe 3 hertz, is trying to backdrive a system, that force feedback is sweeping away almost all of the friction in the system. And, you know, it feels really good, but as soon as you have any kind of impact, you know, the resonance and the mechanical bandwidth of the system is always going to overcome your force feedback. And so I think that any case where you have intermittent contact, whether with a person or with an environment in a running robot or picking up objects, I think that the passive mechanical properties of the system end up, you know, always coming to the front. And so I think that, you know, that's kind of the long explanation behind my idea that it's, you know, that it's really all about the mass, because you're not going to be able to undo that mass. And the way that you might be able to undo that mass is in very select cases, like, you know, low bandwidth, you know, continuous contact, for example. But outside of that, you're kind of stuck with the mechanical system that you have to a large degree.
Well, one add-on point there is what's error, right? So if you have a series elastic actuator, you impact something. If you have enough torque and you can accelerate your motor and you can control at that frequency, you may get some force area and come back down. If you did not have that series impedance, you're going to get a big spike in the force and maybe break things. Aaron Dollar's here. Hi, Aaron.
Sorry. Hi. Good to see some friendly faces that I usually see once or twice a year.
Yeah.
You guys aren't as cute as my kids, but I'll take the change in pace. So.
Yeah, but your kids are with you 24/7 now, aren't they?
Yes, they are.
Mm-hmm.
Matt, you're getting cuter though in your older age, so you have a little grin on you these days too. So.
Thank you.
Matt, did you virtually? Yeah, you did. You virtually changed your background to be probably even messier than.
I just thought what I had, my kitchen looks like a mess. So I looked for something that would neaten it up a little bit.
I was just able to join, so I don't have anything to say yet.
I've got a question, but it might be off topic. Sangbei said something about damping in a transmission being the same thing as inertia in your talk, Sangbei. Can you?
Oh, no, not damping. The force-dependent friction.
Okay, great. Can you?
Yeah,
maybe.
Damping is purely proportional to the velocity, right? So it can't be the same as inertia. Like we loosely define backdrivability should be the impedance, which is inertia, damping, and friction. The damping and friction should be just minimized. There's no trade-off. That's why I pretty much agree with what Peter says. It's all about inertia. But people often mistaken the friction to be always kind of static friction, which is not dominant factor in my opinion. Most friction in the transmissions and machines and robots are pretty much Coulomb friction, which means your friction force is proportional to the end effector force, basically. So if you double the ground action force, all the friction through the gear train and the transmission train is going to be proportional to that force. If you think about the gear friction, that's pretty much Coulomb friction. And even bearing, if you look at bearing frictions, bearing's really good. No, bearing friction are pretty much linear, proportional to the normal force. If you think about that, a component that is proportionally increasing depending on the force, which is basically inertia. So if you have a gear friction in your inertia, and if you play with it from outside, if the friction is 10%, for example, I don't know how the ratio works, but you basically feel like, it's 110% inertia. It's indistinguishable mathematically. That's why that's actually the main reason we choose the low gear ratio with the large motor, even though the motor inertia is actually really big. If you do the proper scaling, I never really mentioned in my talk, but if you do scaling of the motor, if you increase the diameter of the motor and then roll the gear ratio, you can also do reduce diameter of the motor and then increase the gear ratio. If you ignore gear friction, their inertia, apparent inertia actually is the same.
Yeah.
You can design Cheetah 3 with a much smaller motor with a much higher gear ratio, but your reflective inertia should be exactly the same with the same performance, even providing that you have a really high voltage. But in reality, those high gear reduction bring with the much higher friction. Most of them are force-dependent friction, which means your reflective inertia just skyrocket. So that's why a lot of high gear ratio system feels like non-backdrabbable, which means you actually have a much higher inertia than your calculatable inertia.
Michael Poza is posting to the Zoom group chat. Mike, why don't you just, you got your microphone there?
I do. I've just been in and out, so I haven't been paying attention all day. I was just saying that I can read what I said, but I think if you're doing something like locomotion where you're moving a lot, Sangbei, I think it's fair to say that dynamic friction is the thing that matters, and so friction is proportional to the normal force. But if you're in a lower speed regime where you're like in and around zero velocity, I don't think that's true necessarily. I think that's where the stick slip effect start to really matter a lot.
You're operating
Make it
the
very
around
visible.
zero velocity. I don't think it matters which velocity you're running. If a friction is Coulomb friction, which is proportional to normal force.
Except when you're sticking, it's a stick slip transition that I was sort of quibbling with.
Well, I mean that's even harder, to even model. I don't care about is static to dynamic friction. I'm talking about the friction that's proportional to the force. So if a static friction is proportional to normal force, it's going to be Coulomb friction. Dynamic force, friction force is proportional to normal force, is going to be Coulomb friction. So it doesn't matter which regime you are. I guess if you're not moving, inertia is not even in the discussion. So I'm talking about a situation where the acceleration happens, which means you're always moving. So I don't even think about like a stick situation, right? If you feel inertia, which means you have acceleration, you have acceleration, which means you're not sticking, you're always sliding.
Well, one thing's clear, and it had never occurred to me before, is that force-dependent friction certainly really exacerbates any reflected inertia that you've got.
Yeah, that's actually main culprit. Most of the robot, high gear reaction, but it's actually the main culprit is all this force-dependent friction. Because if you think of a manufacturing robot, every bearings are preloaded, everything is preloaded. They don't care too much about energy loss. They don't care about transparency. It's all about the accuracy and then position control. So that's why a manufacturing robot can stop really quickly. It cannot accelerate quickly, but it can decelerate really quickly.
Yeah.
It has tons of energy dump.
Well, here's another question then that for everybody is, what's the relationship between, say, back drivability and efficiency of the transmission? We've been looking at that a lot in terms of thinking about transparency and what are all the things that can make it so that the torque you want isn't the torque you get. And there's these 4 quadrants of operation, right? You're applying torque and moving forward. You're applying torque forward, but moving backwards. You're applying torque backwards, moving forward, and you're applying torque backwards and moving backwards. And if it was straight up efficiency, then it's really predictable how much torque you're losing when you're moving in one direction versus the other direction and so on. But is that the only piece of back drivability? If a transmission is less than 50% efficient, it's not back drivable. If it's more than 50% efficient, it is back drivable. Is that the only
I don't like the coupling the back drivability with the percentage, because usually when people say it's back drivable, not back drivable, we're talking about inertia actually.
Well, yes, I'm just talking about, can you push it and even get it to go? Or
but the 50% argument is actually more like a statistical. Like if it's not like if it's perfect system with the 50% friction, you should be able to push. But if it happened to be 50% around and then gestation got too much and then you can't push anymore. I mean, a lot of non-backdrabbable, seemingly non-backdrabbable system, you can actually push. If you wiggle a little bit, it starts pushing. That's where the stick slip.
Okay, fine. Those are on the 50%, but
yeah. So back drivability, in my opinion, should be replaced by IMF. Really, it's should be about inertia, including friction. So I guess the friction is hard to include unless you do a lot of experiment. But it's governed by inertia, in my opinion.
Back drivability governed by inertia. I don't think I agree. I don't think I either don't understand or I don't agree.
Well, somebody can quantitatively define back drivability to begin with, so we can have a same conversation.
I need to use that one with arguments with my wife, John. I either don't understand or I don't agree. It gives you a lot of outs there. Good.
Yeah. Think about it. Back drivability is such a human term, and then there is actually paper a long time ago. Somebody said, "Oh, back drivability is impedance." And that's inertia, damping, friction. And why do we even talk about damping and friction to begin with? That's not design trade-off issue, right?
I guess when I think of back drivable, I'm ignoring inertia because I don't think if it's, I'm not talking about frequency, for example. So sure, if I try to push it back and forth really fast, inertia is going to matter a lot. But back drivable in terms of, if I'm going to push on it at infinitely slow bandwidth, you know, take a year to ramp my force up, how much do I have to push it in order to have it backdrive? And for a very low efficiency system with a lot of friction, of course, that's going to be a lot.
Sorry about that. Actually, there's actually real definition of backdrivability as a binary. That's actually a mathematical definition of backdrivability. Is either backdrivable or not is the 0-1 case. I can explain by wedge case. Sorry about that. Backdrivability is used such a loose way, in many different ways.
Yeah.
The full right definition of backdrivability should be 0-1.
Well, so is that at the 50% efficiency where your normal force
no.
matches
This is a very clearly defined. If you push on a surface from vertical to vertically,
yeah,
and then your coefficient of friction is higher than your slope, the tangent theta, and then it's non-backdrivable.
That's the 50% then. I mean, if
No. I don't think it's 50%. Let me think. No, it depends on friction coefficient, right?
It's like a worm drive. If the gear angle exceeds the friction cone,
right?
Like it's completely locked in the reverse direction. I think that's what Sangbei is referring to.
Yeah.
Yeah. So think about the case where you have a very steep angle and then very little friction.
Sure.
And your efficiency can be 50%, but it's totally backdrivable. I don't think it's a correlate with the efficiency. I have to double check, but it's
I think if
defined by the
I think that's exactly what it is. So if you are, say you're driving it forward and you're losing 50% to friction, that's the point at which your normal force and the if you were to drive it backwards, you would lose all of the torque you're applying would be lost to the normal force, and you would have none left over for driving it back. I think that's right at the 50% efficiency point.
Yeah, I'm not really sure. It is defined by static calculation, so there's no efficiency issue there. So, and every gear train actually you can check your wedge calculation. So, for example, Youngjae Kim, he's a renowned like hand designer and transmission expert. He actually designed a 60-to-1 gear ratio system with a much better wedge, like backdrivable in a wedge compared to certain other design where it's a non-backdrivable because the wedge situation. So imagine you have a multiple wedge in series, and then if one of the wedge is really bad, it's become non-backdrivable. But if you balance that wedge almost equally, then it becomes backdrivable.
Mm-hmm.
So every transmission you can actually analogous transform into wedge case.
Yeah, so like the coefficient of friction and the gear ratio basically determine
exactly. That's exactly the criteria. Yeah. So vector should be actually 0-1 argument, but we never use that in a oh, this is very backdrivable, or oh, this is not very backdrivable. And again, in my talk, I argued that, like, how do you even say, like, have that kind of conversation when you're comparing 1 kilogram robot to 100 kilogram robot? 1,000 kilogram robot, very backdrivable if you push with the hand.
Well, it depends on the scale of the force that you can apply. So if you have if you can apply like 1,000 newtons and you're trying to push this actuator around, and of course it's hard. Well,
again, but what I'm saying is that think about how we even start even conversation. We usually play with our fingers or finger arms. And then there's no formal definition on that scale, right? So I think the proper way to discuss the backdrivability is the 0-1. And then very simply described by the wedge calculation. And if you want to talk about the real backdrivability issue that we did talk about in the impacts and stuff, IMF is the right thing to do. It's all of inertia, as Peter mentioned and I mentioned in my talk.
Looks like Yifan has his hand up.
Oh yeah, thanks for letting me know. Let me ask a question to pull us back to the topic. I will ask a question about manipulation. So in a lot of videos in today's speaker's talk, I saw a lot of examples where you use a direct drive device or transparent device such as grippers or manipulators. And most of those examples are about showing off the sensitivity delicacy of their actuation. So they will not break anything. They are very sensitive to smaller force. But there is another aspect of advantages of direct drive devices, which is the ability to engage in contact safely and stably, right? So I was wondering, this is a question for all speakers, that do you have experience, and how is your experience on manipulation under external constraints, especially rigid context, and what's the difficulty you are facing, and yeah, basically in general, how was your experience on this kind of problems? Just give you a few examples. Like you can rotate an object between hands, use a compliant manipulator. You can't do that with any traditional industrial robots. That's very difficult. But with the high bandwidth direct drive devices you guys designed, it's possible to do tasks like this. Also, in tasks like rigid body assembly, these are scenarios where the ability to maintain contact safely is very important. So I wonder why we haven't seen many people doing experiments using direct drive device on those tasks.
I'd say it doesn't have to just be direct drive, but sort of any we saw lots of sort of different mechanisms and different actuation techniques. And I think your question is really about sort of how do you sort of maintain contact and sort of contact stability there, and not have your foot skip along the ground or have the object sort of slip out of your grasp.
Yes, yeah, maybe not necessarily maintaining a contact. Sometimes slipping is necessary for a task. So in general, how do you maintain a desired contact mode? I guess that's more precise.
It all comes down to inertia, right? Is that the theme?
Yeah, I think that's, I would say that our conversations have mostly focused around inertia, given this assumption that transparency is most challenging or critical when our actuators are not local to the contact, so like at the hips or the shoulders. I would say that my lab is not a controls lab. We're designing machines, and as we're doing that, we're going towards solutions that have actuators, even in small minor actuators, that are local to the contact. And I think that's something you see as people try to change contact conditions directly. I think it's a complement to the main topic of today, which is when your larger actuators are remote. So I think it's a twofold problem, and they go hand in hand. I don't know if that's exactly answers this current concern or not.
I think the suction grippers is really enforcing this sort of contact stability.
Yeah.
And when I think about contact, the first thing I write down is your normal force, has to be positive, right?
Mm-hmm.
But now that's not true anymore, and that changes a lot of things. Sorry, I cut John off.
Hi, yeah, this is Peter. Just a couple things to add. When we've talked about, well, mass is everything, I think that's mostly in the context of initiating contact. I mean, that's sort of a contact event is a high bandwidth event, and that puts the maximum stress on the system to perform, and mass is the main driver there. But if you have stable contact, right? If a person is grabbing a haptic interface or an arm and moving it, or if you have a grip on an object and you're manipulating it in hand, then I think that's a much easier problem in the sense that what you're really trying to do is you're trying to control the impedance, and so controlling impedance over a much smaller bandwidth is pretty straightforward using a variety of methods. You could have a more of a position source actuator with good force feedback. You could have a more transparent system with an open loop force control, and what gives you good performance in this case is just the ability to have a high dynamic range in impedance. So, you know, being able to have very, very low stiffness and also very high stiffness. And so, for example, you know, inserting a peg into a hole, the remote center of compliance mechanism, you know, is basically a device that perfectly tunes the, you know, the impedance ellipse in such a way that it, you know, is very compliant in one axis and then very stiff in another, or, for example, has a certain coupling. You know, this force couples into this torque, et cetera. And so if you have, you know, by a variety of methods, if you have a manipulator that can exhibit a wide range of impedances, you know, again, within the context of stable contact, you don't need very high bandwidth, right? You know, 10 hertz is perfectly sufficient for many of these tasks. And so if you have the ability to change the impedance of every joint actively, then you can simulate this remote center of compliance device, or you can simulate some other theoretical passive compliance that's suited to the task. And so, you know, if you have a soft manipulator, if you have a compliant manipulator or an under-actuated manipulator, again, that's sort of like a remote center of compliance device. You sort of designed in the perfect passive dynamics, but the problem is, you know, you're stuck with that. So I think that the wanting to have a high transparency manipulator, you know, a rigid manipulator that can act compliant when necessary, is for the case where you have multiple tasks where, you know, you're doing one thing and then you're doing another thing, and you don't want to be stuck with baked in passive properties. You know, if your job is to pick up strawberries on an assembly line, then, you know, a pneumatic soft gripper is absolutely the most perfect thing for that. You know, it's perfectly designed for that task. But you know, you can't then take that gripper and have it start, you know, putting pegs in holes or you know, doing any kind of manipulation that requires higher bandwidth. But yeah, I think the key is that once you have contact, and if you're dealing with a lower range of bandwidth, then the problem becomes much easier. It's that making and breaking contact. You know, it's if I'm going to establish contact, I'm going to reach out and touch something, then that's necessarily a high bandwidth event is that initial contact.
So I wasn't here for a lot of the beginning, so forgive me if I'm repeating anything that was already said, but I like to think of a lot of these issues in terms of the closed loop kinematic chain and how many degrees of freedom and then degrees of actuation you have and so forth. And I think with the majority of cases, you know, whether it's locomotion or manipulation, you end up having fewer degrees of freedom in the kinematic chain than you have actuators. And so you're in this sort of over-constrained, redundant sort of actuation and control regime. And when you're in that regime, you're almost always going to have error. And the amount of error that you have and then can deal with depends a lot on the sort of nature of what you're able to control. So for instance, within hand manipulation task, like you were talking about, if you have high impedance actuators, you're only really controlling position. And if your error is therefore in position, it's going to break. You're either going to not be in contact with the object and drop it, or you're going to, you know, have too much, you know, position and squish it and break it, for instance. Now, practically, you know, there might be some other limitations, or you'd be somewhere in the middle there. But if you have sort of a low impedance, if you're able to do torque control or something like that, the error can be in force. And so what happens then is you can maintain contact by allowing the sort of internal force on the object, or not necessarily allowing it, but that's what's actually going to vary. So you can move the object around and still maintain contact, but you've allowed the force to vary, and the change in force is sort of where that error manifests itself, and that is often acceptable or more acceptable in a contact task, where you're trying to grasp and manipulate an object.
One concept that I'm a bit surprised maybe hasn't come up as much as I thought, or maybe I missed it, but that sort of macro mini combining admittance, impedance at different levels, that might get to solutions that are meaningful in a way, instead of just trying to optimize one particular element. And maybe that's not true for locomotion systems necessarily, but maybe that would be very suitable for manipulation systems.
So there's something I've never understood about macro mini, and maybe you can explain this because you've been a lot closer to the people who've been working on it. So macro mini, as I understand it, is like a big robot arm that's heavy, large actuators, and at the end, much smaller, much lower inertia, much higher frequency kinds of actuators.
Mm-hmm.
But the amount of force you can apply with those big actuators is going to be much larger than the amount of force you can apply with those little tiny actuators. So
yeah,
what's the point? If
yeah.
I want to.
So I think it's you could use the small actuators to essentially elongate the so I'm imagining an impact scenario. So the big actuators coming in, the little actuators could basically act like a spring, but I suppose a very flexible way to control that variability in a much higher bandwidth. But I do agree, you're right, that's going to have limits just for when the forces are smaller. It's not going to operate in the same way once you get past that force limit.
Well, the macro mini that proposed by Stanford group is actually not, it has some issues, and I can't talk too much on right now, but the best example of macro mini is actually your hand. Your arm is actually, if you make a fist, you're gonna be able to, you have to be much careful. Like you don't want to bang your hand on the door, you're gonna bruise. But if you think about your finger, it's actually not that strong. But whenever you need the high force, you use 5 fingers. There's a parallel aspect. So if you properly design it, you can actually get macro mini properly executed, like low impedance, low force. But whenever you have a power, whenever we do like a high power manipulation, we use like power grid. So even industrial robot arm, which is a very high inertia, not good for impact. But if you have a very well designed finger and low impedance, that's where the macro mini concept can really shine. And we talked about this a lot. Like if you have like some magic tube platform, miniaturized tube platform that basically handle the wrist, now you can use industrial robot for many contact-rich task without worrying about or without redesigning entire arm, because no matter what, the arm is going to be heavy. I will try our best to minimize gear ratio, all that. The arm is going to be heavy, and you don't want to impact with anything. So
the point is the mini part is always going to bottom out. Then if you're going to do a big power move, you're not using the mini.
Yeah.
Got it.
So the hand, that's where I keep on saying there's a magic in the hand, and really. Again, I think eventually our discussion is going to the intelligence. I don't know if you are open to talk about what kind of intelligence do we need in the finger. I have a lot to talk about that, a lot of questions to ask, basically. I don't have much to offer.
I think you should ask the questions.
So, this is one of the questions I mentioned. I'm not a manipulation expert, but whenever I think about cost function, this is all these thoughts start from the cost function. I've been working on my student, he graduated, but he's been working on this regularized predictive control, which pretty much a very structured regime to tune the cost function to achieve what we want. And if you really think about what we want, is like locomotion is running well and walk well without falling really well. And how would you even quantify that need in a systematic way? Everybody uses some trajectory tracking. if you put like some random cost function, that doesn't achieve your goal at all. So it takes a lot of time to really get closer to what you really want. That's the process of tuning, basically. And yeah, locomotion maybe can be done that way. When it comes to manipulation, it's just a completely different ball game. And the abstraction, you know, one of my video I show you in my talk was this tray cleaning person who's just throwing tray everywhere, and he basically executes this from cleaning tray abstraction. I need to clean the tray, and all these detailed actions. I can't really put my mind in some sort of optimal trajectory or optimal force control there. And the same thing you can say about my blind apple picking video. Like I throw my hand and then hit some couple apples, try to grasp without knowing anything, and then I ended up contacting 5 more apples, and then I choose one of them, and then ended up choosing worst case, and somehow you manage to dig in and then pull it out. What is optimality there? So what I'm trying to say is, like, we don't even have a proper human language to describe any of these tasks. So I can give an example of like nonsense example where if you have an alien or anything about human culture, but barely understand English is a very abstract sense. You can't describe how to do anything on the phone. You're going to have a phone with the alien. And I'm going to describe how to spread the peanut butter and the peanut butter on the bread. It's not easy to hold well without squeezing it. Peanut butter, it depends on temperature. You have to change how you do it. There's no way you can describe all that action in the phone, because none of these action we ever had a language to communicate. If you think about why we never had a language, because we never needed ever as a human being or animal, because some mirror neuron, whatever, can learn so quickly by looking at them. If you think about how you teach any carpentry or any task, show them, do this, I push a little hard, and then spread it well. Oh, it looks good, right? Listen to my languages. It's unbelievably abstract, and the human understand looking at it, and then there's a few binary cues, you get it. And how on earth we can even make a progress in this complex task without even have a human language, let alone very abstract representation mathematically and so on. A few good examples I think on that discussion is we have a force closure and form closure. I think it's really good terminology and they're well defined, and it represents something very meaningful. I think we need more of those, more than this. Something to do contact, impact, rubbing.
So there is some
practical way.
Yeah.
Mm-hmm.
So some literature around human manipulation do what's called haptic procedures or exploratory procedures. I think that's a good start. There's probably more that we would want to have as roboticists, but we could start from there.
Yeah. So we need more of that in a way that, it's sufficient to communicate human. No, we need more detailed or concrete terminology, which maybe at some point can have a right mathematical representations. And then when you do high level tasks, your whatever optimization or decision maker can mix and choose and, touch now and then rub, or, like you have to have a high level planner, not necessarily like trajectory planning sense. It's more like almost everything is discrete planning. But now you cannot even start having discussion about it, because I don't know even how to describe it with the English, Korean. Some language might be a little better than some other language, but I think this is something we should start thinking about as a community. All we do talk about is force, velocity, acceleration, friction, and force closure, form closure. It's just not. I can't even describe how well.
Sorry, I'm sorry, I didn't mean to cut you off.
Oh, Matt, you're muted. I think you're speaking.
Yeah, I figured it out. Let's see. Well, so I like a lot. I like everything that Songbei said. I think manipulation. I think all generalizations about manipulation are false. If you, there's so many different tasks and I think you can probably, for any generalization somebody asserts about manipulation, you will be able to, if you try, you can construct sort of the adversarial task that proves it wrong. And we just don't think of it that way very often because we get focused on a certain task, which might be like, a mechanical assembly or pick and place little blocks or whatever it is. And then when you open your eyes and look at things like the apples, that's a great film, by the way, going after apples. You see a lot of things that we just can't explain. What actually prompted me to raise my hand was when you said there's no way to describe it in words, and I used to say that, and I used to hear a lot of other people say that about tying your shoes. And then somebody tried it and did it, and it wasn't that bad. So I think, certainly a lot better to explain how to do things when you can show, but I think you can describe it with words. But I don't think that contradicts what you were saying. You were saying we should be trying to do a lot more of that. And so I'm just agreeing with pretty much everything you said.
I found that I found that it really helps. So we've done a bunch of work on trying to pick apart human grasping and manipulation from video and to categorize things. And everybody's familiar with some of the grasping taxonomies, which is only a really small piece of what's going on. But if you just allow yourself to think about it from multiple different reference frames, it kind of helps, in my experience, to kind of help put a little bit more structure on it, right? There's sort of like an object-centric view of what's going on. Then there's sort of a hand-centric view of what's going on. If you look at trying to describe what's happening to the object or what's happening to the hand, or vice versa. And then there's something about sort of the interaction between the two, in terms of like force and that kind of thing. That kind of helps, to add some structure that I found that helps. I will say that things get a lot more difficult to explain when you start to allow yourself to break from an anthropomorphic description of the hand, right? I mean, if I actually take a human hand and what a human's doing, you can describe it in a certain way because you can, label each phalanx, and you can talk about the distal side of it, and you can really, with enough words, get enough detail there. But I think a lot of what we want is something that's a little bit higher level that applies to non-anthropomorphic hands or any kind of hand. And then it gets, a little bit more difficult. But if you do think about things more from I think those kind of three categories, it helps put some structure to it that language could be more easily attached to.
Yeah.
But like Matt said, I mean, it's just really complicated. And every time I've gotten into, we've published a few taxonomies and that kind of thing along these lines. And those are some of the hardest things I've ever done with my lab, because I usually get 4 or 5 of us who really know what we're talking about in the same room, and we really dig in for days, honestly, and argue back and forth. And the only thing that ends up being true is something that's very high level and nondescript generally, and not very interesting then, right? Because you can always find ways to break it. So
on this sort of language question, tying it back to the theme of the workshop, I thinking about this sort of the apple picking example, I think there's some cases where the contact is a lot of the sort of important description of the behavior of, move until your hand touches the coffee mug, right, and then squeeze. And then there's other situations like the apple where the contacts were sort of unimportant, right? Of like, all right, you're going to bump into some apples. I don't need to describe all of those contacts, and it doesn't sort of affect the task. So sort of what do people think about how do we figure out when contact is the sort of critical description of task or the performance metric or what have you, versus when context sort of doesn't matter.
Well, even Apple picking context is important. What I'm saying is that context force is not important. You know, so think about
there were contexts that were
really,
important, but there were also contexts that weren't important. Like you bumped into some other apples, and whether you did or you didn't bump into the other apples.
What is important, what is not important. I think it totally depends on your algorithm. You know, if you look at my example, my algorithm is so dumb. I mean, it's my subconscious, so I can't blame it.
I think you're being hard on yourself. I think you're being hard on yourself. How do we know that it might have been optimal? You just haven't figured out the criterion.
No. Well, I'm not saying it's the dumb overall. If you look at individual decision making, it's not necessarily most optimal. If you if you look at the video, like the first it hit 3 apples, and then if I have my sensor, I'll probably find out the surface normal, and then find the closest distance, and then pick that one. But my hand didn't do it. I just randomly tried to grasp it. And then the next time I'm counting 5 more apples and then choose the worst choice. But overall, it's just unbelievably robust because not necessarily individual force control is good or trajectory is optimal. No, it make a right decision. There's plan A, plan B, plan C, plan Z, plan Z. You know, like we have this crazy hierarchical thing going on all the time. That's my just guess. You know, I'm just kind of, you know, being a lawyer on my subconscious, but. You know, if you think about grabbing a keys from your key, every time you bring key out, your action is going to be different, and we somehow, our subconscious somehow can deal with that. Going back to Aaron's question, what context is important, what is not? I think we need to have some algorithm that can make that decision. This is just very vague answer, but once you have a good, let's say, next better algorithm, we probably can say which one is better or which not, but you know, not much good. I just want to say that the reason why we're like I'm talking about this, we're not having enough language, because most of them are pretty much autonomous, in my opinion, subconscious. And then if you're sitting in the chairman's seat, all these like workers thing automatically happen. You think it's easy. And that's at least what's going on outside robotics community. You know, oh, my son can do it, or my dog can do it. They don't know how to judge what is typical, what is not typical in the robotics, because we tend to make a judgment based on what we can do, what we cannot do. I can play chess very well, but I can pick an apple very easily. Must be easier.
Let's go Avik and then Hannah.
Yeah, I actually completely agree with what Sangbei said, in the sense in that I think the answer to your question, Aaron, is very dependent on the algorithm that's being employed. So for instance, just as an example, I think in a lot of the locomotion like demonstrations we've seen today, we sort of, with the exception, actually, I'll get to the exception in a second, we tend to use kind of simplified models of, trying to just say that we know when we're in contact with the world and when we're not. And obviously, if you do that, the algorithms become quite a bit simpler. You can have very simple solutions, but then you do need to know, and it's very important. And that actually quickly becomes impractical in a lot of manipulation examples, which is actually, I think, one of the things I find quite interesting about manipulation is that, yeah, navigating the kind of the combinatorial explosion of the different contact modes you can have. And I'm not saying there aren't algorithmic solutions to that. Michael Posa has worked on this, and others also, about navigating this complexity. But on the other hand, Rex can obviously perfectly run outdoors without trying to even know what surface, when it's in contact or not. And that's just a different kind of algorithm. And, obviously, just, talking about that Rex example versus like the MIT Cheetah, for instance, there's kind of a difference in its design that sort of ties in with that choice of algorithm, which I also think is quite interesting.
So that's a very important point. When it comes to that racks to more modern like robot, where we use MPC or higher, more complex algorithm. What is that equivalence in manipulation or grasping? That's what we've been thinking about for a long time. it's pretty difficult to even define next target. So a lot of hand manipulation, people are targeting, oh, I want to be like as good as human. I think it's a little too ambitious and it's too much to grasp or wrap my head around. And what is next, the 10 years maybe, like as a community want to achieve? I mentioned this to many people like, Alberto and Ken Goldberg, and we need to have this like, next, I don't even know how to draw the boundary of this is a level 1 difficulty. We need to have that actually, like a level 1 difficulty, like autonomous car, or level 2 difficulty, level 3 difficulty. Again, I'm not sure we are qualified to do that because it's all automatic. So, but at least we started thinking about it so we can set some boundaries. Like Yongjae, have you seen those hand, like the flex hand that got best paper award in ICRA? It's a 1.8 kilograms of 15-degree freedom. It's a nicely backdrivable. There's some friction issue, but if you add a direct contact sensor, that hand is pretty awesome. We just don't have any equivalent algorithm to execute anything near what human can do. So I'm not agreeing that we need the 15-degree freedom hand, something dumber, but I don't even know where to start. Anybody has an idea?
Hannah, you had your hand up?
Yeah, I just wanted to reiterate this idea that in manipulation, yes, there's all these different contact types. And I think forced transparency is essential not only in how we do grasping, but also just as a probe. So our hand is a probe, we're feeling the world, we're doing haptic procedures in order to feel it. And those elements are intuitive. If I give you an object and ask you to tell me how stiff it is, you're probably going to tap it or squeeze it. If I ask you what the texture is, you're going to naturally rub it. And now those two motions are going to excite different degrees of transparency. I don't know how exactly to use that word, but if I tap, I'm extracting different information than if I rub. And so I actually think we need to talk about multiple degrees of transparency and how we sort of utilize and excite those different modes of transparency in this really complex situation. So I actually feel like to complement the grasp taxonomy, we should have like and it might already exist, I would have to look more, but like a haptic procedures classification, maybe expanded. And that could be non-anthropomorphic if needed, I really think.
Yeah.
So real quick, I should point out that we are officially 17 minutes beyond time. And so if people had other workshops or other things to get to, we would certainly understand it if people start to drop off the call here. I think it's been a great discussion. So we're going to keep the Zoom meeting open as long as people are here talking about stuff. But I just wanted to point out that nominally the workshop is wrapping up, but I don't want to cut off this great discussion. I think we'll go to Peter Whitney on the phone, unless there's two phone people.
Yeah, Sangbei, I just had a thought when you were describing the Apple example, and it reminded me of a discussion that we had about Cheetah 2, the optimizer to jump over an obstacle. And you were describing how your objective function was 0. And so really the optimal solution for you was to just grab the first feasible solution. So really thinking about constraint-based optimization rather than objective function-based optimization. So I wonder if your Apple case, you're just shoving your hand in and you're just perturbing or adding noise, or just randomly exploring possible solutions until you found closure, till you found a feasible solution, and then you picked that one.
Yes. So this is something I've been talking to many people, but not necessarily politically correct or good for writing paper. It's actually, if you talk to biologists, they actually start talking. They've been talking about this all the time. Like none of the animals are optimal. None of the animal behaviors are optimal. They're just good enough to survive, or at the time. They might not be good enough at some point extinct, but that's exactly what it is. The thanks for bringing that up. I forgot about that, like cheetah 2 jumping over obstacle running jump. My postdoc say like the cost function is 0. Like, why did you do that? And it's like, well, feasibility search is much faster than optimality, and why do you care if you jump over what is optimal height whatsoever? I don't care about energy when I jump over. That's exactly the good example where when you pick an apple, I probably pick an apple 100 times differently, and none of them are optimal. I don't care because I can pick an apple. So this has to be feasibility search and as reasonable, good enough, right? The constraint. That particular video, it turns out that my hand was very lazy in moving in transverse direction. Was only want to go like prismatic direction and then let the finger do the whole job. But I think this is a very important point. Like a lot of tasks, it's important to find the good enough feasible solution with a reasonable time rather than every single thing optimal. And the plan BC, like the hierarchical combinatory like explosion is actually the challenge rather than finding optimal, finding better sensor, more accurate sensor, or better force sensor. Those are, I think, is not as important than discrete decision making, which again, I talk as introduced, this is still very difficult to even think about. Like I talk about this, like when I pick up this bottle and then manipulate, I can change my force probably order of magnitude. I can achieve the same thing, and then probably indistinguishable for whoever watching. Like there's a range of things I can do without changing my abstract goal. So we need better representation of these tasks, but I don't want to try to think about everything human do. Again, it's going to be impossible. We need to find like smaller subset of tasks, what we want the robot to do. And maybe we can start talking about languages or representation of abstraction. And but again,
Oh yeah, so since we've got all these people so knowledgeable in this area, it suddenly dawned on me I should be asking a question that's been bothering me for some time. So one way of sort of minimizing mass is, you'd like to have a spring like at the very end of your effector, you might say. But springs have mass, and so if you really want to do it right, you would have like a teeny tiny spring and then a bigger spring and then a bigger spring. And basically that's what you get if you have like a foam ball, right? So it seems like, aha, the ideal fingertip would be a foam ball. And then the next thought that occurs to me is, wow, I really, really would not want to wrap my hands in foam. Okay, it's gonna be hell for the bandwidth. I'm not gonna be able to juggle or do whatever I want to do at a certain frequency. And so one answer to that is, okay, you have foam on one side and you have something hard on the other side. And so that's kind of neat how you can just change that by changing your configuration. But the other thing, the thing I wanted to ask about was that a long time ago, I heard Vincent, what's his name? The guy at in Paris. I can't think of his name. Anyway, he builds haptic illusions, and Vincent Hayward. One of the things he said was that the human fingertip has important viscoelastic properties. And it occurs to me that viscoelasticity might be a way of having foam on your fingertips and still maybe retain some of the high frequency thing that you want. And I've played a couple of times with doing little experiments. You know that there's that foam rubber called that EAR makes that's kind of got some viscoelastic it's got memory foam basically, right? So I played a couple of games with memory foam trying to see if I get anywhere, and that doesn't, those experiments have never turned out very well. And so I'm really curious whether any of you have thought along these lines and gotten anywhere with that line of thinking.
Avik, you had different hierarchical compliances on the feet of the robots, right?
I mean, to be honest, I guess the hierarchy, we try to put as much of it in software as possible, because of the difficulty of tuning this. I mean, yes, probably we would like some of these, compliance pyramids, or I'm not quite sure, if they're describable by a single set of dynamics, or maybe it's task specific in the sense of, yeah, maybe you just want to be stiff for some time and then stop being stiff and be softer. Yeah, I think the best we know how to do, at least, is to stick with software for enforcing as much of that as possible. For the software has its limits. We've talked about the bandwidth limitations. After some point, if you hit the ground with a leg that's very stiff, like a metal leg or something like that, it is going to bounce, and there's nothing the software can do about that. So you need to do something mechanical to get rid of that. But after the software can catch up, so if it's something that can be stabilized at a kilohertz or something, we prefer to do the rest in software.
Yeah, I don't have a complete answer, but I can tell what we've been trying. So in the leg robot, we want the things that stick to the ground, the foot to stick to the ground, trying to minimize the bouncing. So we use a sorbothane inside of the Cheetah 2 leg.
Sorbothane, that's the
much energy, so it reduces. Yeah. Oh, yeah. And Cheetah 2 was the case where we were trying to achieve high speed, so we actually ended up taking out the sorbothane and then replaced with rubber. But later on, we tried even a sandbag. Actually, it's a very highly dissipative system that can just stick to the ground. It worked pretty well. We just had a trouble fabricating well. When it comes to manipulation, I think, as Matt mentioned, we want something like a finger that's very soft touch, and then you can squeeze, absorb some energy. I mean, if imagine this is another kind of difficult thing to replicate. If you touch your fingertip, it's extremely soft. It's almost a sontofu level. And then if you do the same thing on your feet, your feet are extremely soft by touching it. But you know how much force your feet can handle and run and then turn left and so on, because it's a very nonlinear. It's there's a skin and there's a collagens and when you manipulate things, when you touch, it's very soft, very hard to keep it stiff. But we have this degree of freedom plus intelligence. We can bring up the tip where the fingernails are. Now your contact becomes very stiff, which is a luxurious thing to even think about when you have a manipulation. So I don't have a good answer, but it's really tricky thing to replicate in the robotics world. And there's actually a way to fabricate it as a glass fiber cover, and then you have a multiple gel inside and a stiff rubber outside. The annoying thing is once you wear out or get damaged, you have to refabricate that. It's just so difficult. That's why we ended up having this piece of rubber at the end, because I want to replace easily, cheaply.
Feifei, you have a question?
Yeah, I more want to sort of comment on what Matt and Sanbei had been saying, because I found the idea of I don't work on manipulation, but I work on a lot of the granular stuff. So I think we've been assuming the trade-off, right, come from the mechanical stability versus the sensing bandwidth, is we are assuming we have one constant property across the entire, either it's the manipulator or the foot. But I think one idea that the Matt has mentioned maybe start to inspire me to think about our fingers, or maybe some other things that we desire, it might not be one constant property that's either stiff or compliant, that's either very, very vectorable or not. But it's probably a combination of a lot. And the sandbag thing that I was thinking about, sand to me, it's a very inspirational, because it can be somewhere in between fluid-like versus solid-like, and they are collective systems. So you don't have one constant property globally. And if we can, sort of like expand on that idea, I think if we make something, which I'm sort of trying to do, is to make something that can change in between. And I think one other aspect that's important when I bring up this is I consider a lot of not just like our side of property, our manipulator, our locomotion appendage, but also the environment. What are we trying to engage to? What are we trying to couple into? And I think that's something in terms of robustness. It takes a lot about, not just designing the perfect system that works for all scenarios, but do you have this this way of understanding what's the optimal thing that you need right now for your current task? We've been talking about it's everything's task specific. So on that, I think, when I think of these tasks, locomotion or manipulation, I think of, can we use something that allows us to have some flexibility in switching on the spectrum of more, more towards one end versus the other. So that's just something, your great conversation questions inspire me to think about. Yeah.
I think you said that really well. I find it so fascinating, this idea of the details of the fingertip. Because I mean, there's a part of me that wonders if, well, is most, if not all, soft human tissue viscoelastic? Is it just like a function of, we need something squishy there to protect our bones, and it just happens to be that the best option was viscoelastic? I don't know if I can see a super clear role. I do think I like what Feifei just said about sort of how the tissue might be changing its properties based on the different ways you load it. And I immediately think of like, your skin in shear is actually quite stiff when you're touching lightly, but then when you squish it, it's quite squishy in shear. And that just reminds me of like when you rub something to understand its texture, you do it with a really light touch. And probably that's because you want to have a stiff, high transparency local system. So yeah, thanks for that, Feifei.
The other thing I like about everyone asking questions about fingertips is then watching all of you sit there doing this while people are answering the question. And like, oh, what random object do I have around that I can play with?
That's a good point. The main function of fingers is actually to count.
And yet I didn't see anyone in the locomotion section get up and run back and forth in front of their camera. So.
Somebody should design a jamming gripper attached on each fingertip with the one pneumatic source.
I think somebody did that. No?
Yeah.
Oh, somebody already did that? Yeah.
John Amond made a thing that's a kind of gripper that has the jamming stuff at the fingertips. It's interesting. It's a nice idea.
Awesome.
Yeah, I gotta find that.
Yeah, soft touch, and then you can lock in and then get stiffness. That's
it's
great.
Interesting. Yeah.
Yeah, we should just go beyond biomimetics. You should do whatever we can do. You should attach a suction cup each fingertip. And
well, yeah. So I think suction cups are
incredible.
We had a conversation about that before the project really got going. So yeah.
As far as I know, the picking the warehouse, some company use multiple suction cup, different kind, and then there's some simple logic. If you have a too low pressure, just shut off. So reserve the pressure and so on. There's many things going on there. which
Yeah,
is
there's a guy at Maryland. I forgot his name now.
Chad Kessens.
Did
the self-sealing ones?
Yeah.
Yeah. Chad Kessens. I think he's at ARL now.
mechanical.
Yeah, so, I mean, there's a couple of designs actually of if you're touching something, open the valve and let the suction air come in, and then if you're not touching something, it's sealed, and so it sort of only engages the suction cup once you touch, and so then it's sort of the question is like how much force do you need to engage that and disengage and everything, but yeah, he's got some great examples where you can now have lots of suction cups and then smack it down and whatever is touching starts sucking, and so you don't have to have as precise placement of the suction cups. One of Matt's students was in my class this past semester, built a sort of octopus gripper with multiple suction cups where they just had to have a pressure sensor and decide which ones a lot of pressure sensors and a lot of valves and just turn off the ones that were open.
Can you repeat the name, Maryland person? I just want to know the name.
I'll get the right spelling even better.
Just the chat. Just throw in the chat. Thanks.
Kessens.
I got a question earlier about sort of whether because I did the suction underwater. How does that translate to air? One big difference is your pumps can be much smaller underwater. You can get a lot more flow out of a much smaller pump when you're working underwater, and it's because of the viscous density differences. So yeah, I think in air you're going to get these systems where you have one big pump with many valves. Underwater you might actually have a system like we do where you just have a pump per orifice. So those scales are quite different.
I mean, an octopus, the pump is just sort of into forming the shape of the cup, right? Yeah. Huh. Well, I think I'll quit.
Yeah. Thanks for the 20 of you that stuck around extra bonus time here.
It was fun. Thanks, Aaron, and thanks, Ankit. My name's on there as an organizer, but I didn't do anything. I suddenly realized at the last second that I should probably show up, and I'm really glad I did. This was fun. So,
yeah, this was a
thanks
great
for
workshop.
organizer. Thank you.
Thank you.
Definitely learned a lot. Thank you.
Thanks everyone for coming and speaking up.
Bye, y'all.
All right.
Bye.
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 See you later.
Goodbye. See you. Thanks for organizing.